Long before satellites mapped the globe, before calculators crunched numbers, and before clocks ticked with digital precision, there existed a world where knowledge was carved in brass, cast in bronze, and drawn on parchment. A world tuned not by silicon chips, but by human ingenuity. Picture this: a scholar in a candlelit room, turning an astrolabe beneath the stars, calculating the hour from shadows cast by the sun, or a sailor on a moonless night, guided only by a handheld instrument aligned with the North Star. These were the moments that defined an era of discovery, an age when curiosity was measured not in megapixels, but in hand-crafted marvels that decoded the very fabric of the universe. What if I told you that many of these instruments, these beautiful, intricate tools, have been lost to history, overshadowed by the very science they helped create? Today, we're going to rediscover them together. We're talking about 26 lost instruments that tuned our world long before modern science even existed. From devices that predicted celestial events to those that measured the flow of tides and time, these artifacts weren't just clever gadgets. They were the foundation upon which our understanding of nature was built. They guided explorers across unknown oceans, helped farmers plant by the seasons, enabled artists to capture perspective, and even let philosophers argue about the music of the spheres. This isn't just a story about objects. It's about the people who made them, the cultures that refined them, and the universal human drive to make sense of the world. Over the course of this video, we'll uncover how these tools worked, why they mattered, and what they can teach us about innovation today. You'll see how a simple disk of metal could serve as an ancient computer, how interlocking rings modeled the cosmos, and how paper volvelles acted like interactive apps centuries before the digital age. By the end, I hope you'll look at the past not as a distant memory, but as a living library of ideas, each instrument a key that unlocked a door we're still walking through today. So come with me on this journey back in time to an age of wonder crafted by hand, and let's uncover the tools that quietly, brilliantly tuned our world. To truly grasp the brilliance of these lost instruments, we must first step into the minds of those who created them. The medieval period, often mischaracterized as a dark age of stagnation, was in reality a vibrant tapestry of intellectual exchange and technological ambition. From the bustling scriptoria of European monasteries to the advanced observatories of the Islamic world and the sophisticated courts of imperial China, a shared thirst for understanding the natural world was driving innovation forward. This was an era where the lines between disciplines were beautifully blurred. A philosopher might also be an astronomer, a physician could be an alchemist, and a craftsman was undoubtedly an artist and an engineer. Their work wasn't segmented into neat categories like we have today. Instead, it was a holistic pursuit of knowledge, deeply interwoven with philosophical inquiry and very often spiritual devotion. They looked at the heavens not just to chart stars, but to understand humanity's place within a grand, divine cosmos. This unique worldview didn't hinder their science, it fueled it, inspiring them to create tools that could measure, quantify, and make tangible the mysteries of creation itself. Imagine the immense challenge they faced. We live in a world of digital precision, where a smartphone in your pocket can access atomic clocks and global positioning satellites. They had none of that. There were no standardized units of measurement that were consistent from one region to another, no factories to produce identical components, and certainly no computers to handle complex calculations. Every single measurement, every gear tooth in a clock, every engraved line on an astrolabe had to be conceived, calculated, and crafted entirely by hand. This constraint demanded not just intelligence, but an extraordinary level of ingenuity and patience. A scholar couldn't simply run a simulation. They had to build a physical model of the universe. A navigator couldn't pull up a GPS coordinate. They had to learn to read the subtle language of the stars, the sun, and the ocean swells using handheld devices of their own invention. This lack of existing technology wasn't a barrier. It was the very catalyst that sparked some of the most elegant and enduring solutions in human history. What's perhaps most fascinating is how these innovations flowed along the trade routes of the known world. Knowledge was the ultimate commodity. A design for a new type of quadrant would travel from Baghdad to Cordoba, be refined by a Spanish craftsman, and eventually make its way to a scholar in Paris. Chinese advancements in clockwork and magnetism would slowly influence European technology. This was a truly global endeavor, a silent collaboration across cultures and centuries. The instruments they produced were therefore not the product of one isolated genius, but rather the cumulative achievement of countless unnamed individuals, each adding their own insight and improvement. They were built to solve the most pressing problems of their time, knowing when to pray, when to plant, how to navigate to new lands for trade, and how to heal the sick. This practical urgency, combined with a deep philosophical curiosity, created the perfect conditions for a golden age of instrumentation. These devices were the bridges between abstract theory and tangible reality, the keys that unlocked a more measurable, predictable, and understandable world. They set in motion the very principles of observation and experimentation that would, centuries later, blossom into the scientific revolution. With this context in mind, we can now fully appreciate the first and perhaps most iconic of these revolutionary tools. Picture a medieval astronomer, perhaps in a quiet courtyard under a blanket of stars, holding a beautifully crafted brass disc. This is the astrolabe, a device so ingeniously designed that it has been called the computer of the ancient world. More than just a tool, it was a portable model of the universe, a masterpiece of metalwork and mathematical precision that could fit in the palm of your hand. Its face was a complex map of the heavens, etched with concentric circles, delicate curves, and finely pointed markers representing the brightest stars. But this was no simple decorative object. It was a functional instrument capable of answering some of the most pressing questions of the age. By simply aligning its movable parts with the observed sky, a user could tell the time with remarkable accuracy, predict when the sun would rise or set on any given day, determine their latitude for navigation, and even cast horoscopes. It condensed the vast, incomprehensible cosmos into a manageable, rotating disk, putting the power of celestial prediction literally at one's fingertips. The true genius of the astrolabe lay in its layered design. Think of it as an early form of sophisticated software, but made entirely of physical components. At its heart was a central disk called the mater, or mother, which held a series of interchangeable plates. Each plate was custom etched for a specific latitude, mapping the local horizon and the altitude of stars for that particular location. On top of these plates sat the reter, a breathtakingly intricate openwork disk that represented the fixed stars and the ecliptic path of the sun. This reter was like a complex clock hand. By rotating it, you advanced the positions of the celestial bodies. Overlaying everything was a ruled pointer called the alidade, used for sighting the actual height of a star or the sun above the horizon. The back of the device was just as important, often featuring a calendar, a scale of degrees, and a shadow square for trigonometric calculations. This harmonious combination of parts allowed a scholar to solve problems in spherical astronomy that would otherwise require lengthy, complex calculations, making it an essential instrument for anyone who looked to the sky for answers. Its development was a testament to international collaboration long before the concept was commonplace. While its origins are often traced back to Hellenistic Greece, particularly the work of astronomers like Hipparchus, it was scholars in the Islamic world who refined the astrolabe into its most sophisticated and widespread form. In the vibrant intellectual centers of Baghdad, Persia, and Al-Andalus, scientists and craftsmen perfected its design, writing detailed instruction manuals and pushing its capabilities to new limits. From there, knowledge of the astrolabe spread into medieval Europe, where it became a cornerstone of scholarly study. This journey made it a universal symbol of learning, a tool that transcended language, culture, and religion. It was as at home in the hands of a Muslim astronomer determining prayer times as it was with a Christian monk calculating the date of Easter or a European sailor navigating the Mediterranean. This cross-cultural exchange embedded within the astrolabe reminds us that the pursuit of knowledge has always been a unifying human endeavor. For all its complexity, operating the astrolabe was an intimate dance between the user and the cosmos. The process began by measuring the altitude of a known star or the sun. The user would hold the instrument by a ring at the top, allowing it to hang vertically. Then, using the alidade on the back as a sighting tool, they would line up the two pointers with the celestial body. Once the measurement was taken, the user would flip the astrolabe over and rotate the rete until the marker for that specific star aligned with the altitude ring on the plate for their latitude. Instantly, the entire simulated night sky would be set for that exact moment. They could then read off the local time, see what stars were rising and setting, and determine the positions of other celestial bodies. This elegant interaction of observation, alignment, and revelation turned abstract theory into tangible understanding. It empowered individuals to navigate not just the seas, but time itself, solidifying the astrolabe's legacy as one of the most profound and beautiful instruments ever created. If the astrolabe was the handheld computer of the medieval world, then the Armillary sphere was its grand, immersive planetarium. This magnificent instrument transformed the abstract concept of the cosmos into a tangible, three-dimensional model that one could literally reach out and touch. Picture a skeletal globe composed of multiple graduated rings, all intersecting at precise angles and rotating around a central axis. These rings represented the most fundamental circles of the celestial sphere: the equator, the ecliptic path of the sun, and the meridians. At the very center sat a small sphere representing the Earth, firmly placing our world within a majestic, mechanical universe. Unlike the portable astrolabe, the Armillary sphere was often a large, impressive centerpiece in an observatory or a wealthy scholar's library, a stunning testament to both astronomical knowledge and exquisite metalworking skill. It was a dynamic sculpture of the heavens, designed not just to calculate but to inspire awe and understanding of the cosmic architecture believed to govern everything from the changing seasons to the tides. The intellectual heritage of this device stretches back to the ancient Greek astronomers, but it was Claudius Ptolemy in the 2nd century who truly systematized its principles in his great work, the Almagest. His geocentric model of the universe, with the Earth motionless at the center and the planets and stars embedded in a series of revolving crystalline spheres, provided the perfect theoretical framework for the Armillary sphere's physical design. Medieval scholars across the world eagerly adopted and refined this concept. In China, during the Song dynasty, brilliant engineers like Su Song and Guo Shaojing constructed enormous, sophisticated armillary spheres driven by intricate clockwork mechanisms, integrating them into massive water-powered astronomical clocks. Meanwhile, in Europe, as knowledge from the Islamic world filtered westward, the instrument became a cornerstone of the medieval university curriculum. It served as the ultimate visual aid, allowing a teacher to physically demonstrate complex concepts like the precession of the equinoxes, the reason for the seasons, and the apparent retrograde motion of the planets, making the invisible patterns of the sky suddenly visible and comprehensible. Operating this instrument was a deeply hands-on process. An astronomer would carefully adjust the various rings to match the current celestial coordinates. By aligning the central axis with the Earth's polar axis and setting the ecliptic ring to the Sun's position along the zodiac, the entire apparatus became a calibrated model of the sky for that specific moment. One could then simulate the daily rotation of the heavens by turning the entire assembly, or track the Sun's slower annual journey along the ecliptic. This allowed for remarkably accurate predictions of solar and lunar eclipses, the solstices, and the equinoxes. It was a powerful calculating tool, but its true genius lay in its ability to educate. A student could see, right before their eyes, why the sun was higher in the sky in summer and lower in winter, or how the moon's path intersected with the sun's to create the potential for an eclipse. It made the theoretical practical and the complex simple, fostering a profound intuitive grasp of celestial mechanics. Beyond its practical and educational uses, the Armillary sphere held deep philosophical and symbolic significance. It was a physical manifestation of the medieval worldview, a harmonious, ordered, and geocentric universe created by a divine architect. The perfect circles and precise movements reflected the belief in a cosmos governed by mathematical perfection and natural law. This blend of science, art, and philosophy is what makes the instrument so captivating. It wasn't just a cold, calculating machine. It was a work of art that represented humanity's place in the grand scheme of creation. Its enduring legacy is evident in its influence on later instruments, most notably the orrery, which would model a heliocentric solar system, and its symbolic power is still felt today, as the Armillary sphere remains a common feature in heraldry and university seals, a timeless emblem of astronomical exploration and the enduring human quest to understand the universe. While the Armillary sphere brought the cosmos down to a scholar's study, the challenges of navigation demanded a tool that could travel anywhere, especially onto the pitching deck of a ship in the middle of a vast black ocean. This is where the Nocturnal or Noctolabe comes into its own. Imagine a sailor far from any coastline, with no landmarks to guide him, and only the endless in-sky expanse of the sea and sky. His most precious commodity is not food or water in that moment, but accurate time. Knowing the hour is the key to estimating his longitude, his progress east or west. Yet the gentle rocking of the ship makes delicate instruments with liquid or complex gearing nearly useless. The solution was brilliantly simple, a device that used the one fixed, reliable point in the entire northern hemisphere, the North Star Polaris, as its anchor. The Nocturnal transformed this unmoving celestial beacon into a 24-hour clock hand, allowing a navigator to tell time with nothing more than the stars overhead. Its design was an exercise in elegant minimalism, typically crafted from durable, affordable wood like boxwood or from a single sheet of brass. The Nocturnal consisted of 2 or 3 concentric discs of different sizes, all pinned together at the center so they could rotate independently. The largest outer disc, often notched around its edge for a better grip, represented the calendar year marked with the months and days. A second, medium-sized disc was engraved with the hours of the night. The smallest inner disc usually featured a sighting hole in its center and a pointer that extended outwards. Despite its simple appearance, the craftsmanship involved was precise. The markings had to be carefully calculated and engraved to ensure accuracy, making each nocturnal a hand-calculated masterpiece. Its beauty lay in its lack of moving parts that could break or mechanisms that could jam. It was robust, portable, and entirely self-contained, requiring no light source to operate, a critical feature for maintaining night vision on a dark ship. Using the instrument was a quiet ritual under the stars. First, the navigator would align the current date on the calendar ring with a specific reference mark. Then, holding the device upright, he would thread a short string or leather thong attached to the center through the sighting hole, dangling the nocturnal so it could hang perfectly vertical. The most crucial step came next, finding the two-pointer stars in the Big Dipper constellation, often called the Guardians or Pointers, as they circled Polaris. He would then carefully rotate the hour disk until its extended arm precisely lined up with these two stars. With everything now set for the date and the position of the circumpolar stars, he could finally read the time. The pointer on the smallest disk, now aligned with Polaris, would indicate the current hour on the engraved scale of the middle disk. This entire process converted the slow, constant rotation of the night sky around the celestial pole into a readable, digital-like display long before such a concept existed. The nocturnal's true historical impact was felt most profoundly during the Age of Discovery. Explorers venturing across the Atlantic or around the Cape of Good Hope relied on a patchwork of methods to navigate. Latitude, their north-south position, could be found relatively easily by measuring the height of Polaris above the horizon. Longitude, however, was a nightmare. Without an accurate timekeeper that could maintain its rhythm on a long, turbulent voyage, sailors had to estimate their east-west progress through a technique called dead reckoning, basically guessing their speed and direction over time, which was wildly inaccurate. The nocturnal provided a way to check and correct these estimates. By giving them a reliable local time reading each night, navigators could better calculate how far they had traveled since their last known position. It was a vital piece of the navigational puzzle, helping to guide vessels like those of Columbus and da Gama toward their historic destinations and preventing countless ships from becoming hopelessly lost. What makes the Nocturnal so remarkable is its perfect demonstration of necessity-driven innovation. It wasn't invented in a university by a theoretician. It was almost certainly developed and refined by practical mariners themselves, solving a dire problem with the materials and knowledge they had at hand. It represents a different, equally important strand of medieval science, one born from direct experience and the urgent need to overcome a real-world challenge. This humble tool, often overlooked in favor of more complex brass instruments, embodies the cleverness of applying abstract astronomical principles to the gritty reality of life at sea. Its operation required no deep mathematical knowledge, just careful observation and a steady hand, making celestial navigation accessible to countless sailors. In doing so, it helped weave a web of safe passage across the oceans, connecting continents and cultures in a way that was only possible by first learning to tell time from the silent, watchful stars. While the Nocturnal mastered the night, the day belonged to an instrument so common it often blends into the background of history, the sundial. Far more than just decorative garden ornaments, these were the primary timekeeping devices for entire societies, the rhythmic heartbeat of daily medieval life. Their operation was a beautiful lesson in fundamental physics, harnessing the one constant everyone could see, the sun's journey across the sky, and translating it into the universal language of time through the silent, creeping motion of a shadow. From the moment the first sliver of light hit a village square to the long shadows of dusk, the sundial provided a reliable, public, and deeply personal measure of the day's progress. It synchronized the community, telling the farmer when to break for lunch, the monk when to sing the divine office, the merchant when the markets would open, and the mother when to expect her family home. In an age before personal watches, the sundial was the clock on the wall for an entire town. The sheer variety of sundial designs is a testament to medieval ingenuity and their deep understanding of spherical astronomy. The most familiar is the horizontal dial, a flat plate with a triangular gnomon, the part that casts the shadow pointing toward the celestial pole. But craftsmen also created vertical dials mounted on the south-facing walls of churches and cathedrals, turning entire buildings into giant timepieces. More sophisticated still were equatorial sundials, where the dial plate was set parallel to the Earth's equator and the gnomon perpendicular to it, making the hour lines perfectly equidistant. For the traveler, there were portable pocket sundials, often combined with a magnetic compass to ensure they were correctly oriented. Each of these designs had to be meticulously calculated and crafted for a specific latitude. A sundial made for Paris would tell time inaccurately in Rome because the sun's path across the sky is different. This meant every city, every monastery, even every wealthy estate required a custom-made instrument, each one a unique product of local knowledge and skilled craftsmanship. Beyond their function, sundials were canvases for art and philosophy. They were rarely plain objects. The dial plates were often adorned with intricate engravings, from floral patterns and mythical beasts to Latin mottos that reflected on the nature of time itself. Phrases like solis meus umbra regit, I am ruled by the shadow of the sun, or the more poignant umbra sumus, we are shadows, served as daily memento mori, reminders of life's fleeting nature. This fusion of art, science, and meditation elevated the sundial from a simple tool to a cultural touchstone. It wasn't just telling the hour, it was prompting reflection on how those hours were spent. This philosophical layer connected the user not just to the mechanical passage of time, but to a deeper, almost spiritual rhythm governed by the heavens. The construction of an accurate sundial was anything but simple. It required the dialist to possess a working knowledge of astronomy to understand the sun's changing declination throughout the year, and a command of geometry to project the complex curves of the celestial sphere onto a flat plane. The gnomon's angle had to precisely match the latitude of its location, and the hour lines had to account for the equation of time, the fact that solar time and clock time differ slightly throughout the year due to the Earth's elliptical orbit. This was high-level applied mathematics made solid in brass or stone. A well-made sundial could achieve an accuracy within a few minutes, a remarkable feat for a device with no moving parts. This precision made it the authoritative time standard for centuries, used to set and verify the mechanical clocks that began to appear in town bell towers towards the end of the medieval period. The sundial's legacy is a profound one. It represents humanity's first successful attempt to impose order on the day, to quantify the unquantifiable flow of time using the most fundamental natural marker available. It grounded daily life in the cosmic cycle, creating a tangible link between human activity and the motion of the Earth, while eventually superseded by more consistent mechanical and digital timekeepers. The principle of the sundial remains eternally true. It was the foundational timekeeper that taught us to segment our days, and its quiet, shadowy measurement of sunlight beautifully sets the stage for an instrument that performed a different kind of magic with light altogether. But the quest to measure and understand the world wasn't confined to the grand scales of the cosmos or the steady rhythm of time. It also reached into the very nature of perception itself. Imagine stepping into a completely darkened chamber, a room sealed against the light except for a single, tiny pinhole in one wall. On the opposite wall, a miraculous scene slowly swims into focus. The world outside, trees swaying in the wind, people walking past, clouds drifting in the sky, but everything is upside down and moving in reverse. This was the captivating experience of the camera obscura, a phenomenon that blurred the line between natural magic and rigorous scientific inquiry. For medieval scholars, this wasn't just a parlor trick. It was a profound demonstration of a fundamental natural law, a living laboratory that revealed the straight-line travel of light and the very principles that would one day make photography possible. It proved that the universe operated on consistent, observable rules, and that by creating the right conditions, humans could capture and study those rules in action. The foundational understanding of this device owes a great debt to the brilliant Iraqi scientist Ibn al-Haytham, known in the West as Al-Hazan. Working during the Islamic Golden Age in the 11th century, he moved beyond earlier Greek ideas that vision was caused by rays emanating from the eye. Instead, through meticulous experimentation with darkened rooms and light passing through apertures, he correctly argued that light itself travels in straight lines from objects into the eye. His seminal work, The Book of Optics, detailed how an inverted image is formed when light rays cross through a small opening, providing the first truly scientific explanation for the camera obscura effect. He even used the device to safely observe solar eclipses, projecting the image of the partially obscured sun onto a surface to avoid damaging his eyesight. This methodical approach transformed the camera obscura from a curious observation into a validated scientific instrument, a tool for testing hypotheses about the nature of reality. As knowledge of this principle spread into medieval Europe, its applications began to diversify in fascinating ways. Astronomers continued to use it for safe solar observation, but artists and architects saw a different potential. By the late Middle Ages and into the Renaissance, portable versions of the camera obscura were developed, often tent-like structures or wooden boxes with a lens fitted into the pinhole to sharpen the image. An artist could step inside this portable darkroom and trace the beautifully precise, perfectly proportioned scene projected onto a sheet of paper or a canvas. This was a revolutionary aid for mastering perspective, a complex mathematical challenge that had long plagued painters trying to create realistic depth in their work. The camera obscura provided a cheat sheet from nature itself, allowing artists to understand how lines converge and how scale diminishes with distance. It's believed that masters from Jan Vermeer to Canaletto used such devices to achieve the breathtaking luminosity and architectural accuracy in their work, forever changing the course of Western art. The true legacy of the camera obscura, however, is its role as a philosophical gateway. It presented a powerful metaphor for human understanding. The outside world is real and knowable, and our perception of it, while sometimes inverted or distorted, can be corrected through reason and the right tools. It stood as a physical rebuttal to superstition, demonstrating that even the most magical-seeming effects had a rational, mechanical explanation rooted in the behavior of light. This shift in thinking was crucial. It encouraged a hands-on, experimental approach to knowledge, showing that by manipulating the environment, by darkening a room and piercing a hole, one could isolate and study a natural phenomenon. This same spirit of experimental manipulation would fuel the entire scientific revolution. The camera obscura was, in essence, the primordial ancestor of every imaging device that followed. Its basic principle lies at the heart of the photographic camera, the telescope, and even the human eye, serving as a timeless reminder that sometimes the most profound discoveries begin by simply stepping into the dark and looking at the world projected in a new light. After exploring the magic of capturing light itself, we turn to an instrument that mastered the art of measurement with beautiful, geometric precision. Envision a craftsman on a cathedral rooftop or a sailor on a ship's deck, holding a simple quarter circle of wood or brass. From its curved edge radiates a fan of finely engraved lines, and from its apex dangles a weighted string, a plumb bob. This is the quadrant, a device that turned the vast, immeasurable sky into a grid of calculable angles, bringing the abstract power of trigonometry into the hands of practical problem solvers. Its fundamental purpose was deceptively straightforward: to measure the altitude or height above the horizon of any object, be it a star, a planet, or the summit of a distant tower. By doing so, it became one of the most versatile and indispensable tools across multiple fields, a true workhorse of medieval science and commerce that translated the arc of the heavens into actionable data on Earth. The elegance of the quadrant lies in its direct application of basic geometry. The instrument itself is a physical representation of a 90-degree angle, a quarter of a full circle. The weighted string, hanging freely due to gravity, acted as a constant vertical reference against this graduated scale. To take a measurement, a user would simply sight the top of a star or a building along the upper edge of the instrument. The plumb bob, unaffected by the user's movement, would swing and then settle. The point where the string crossed the engraved scale on the curved edge gave the altitude angle in degrees. A reading of 45 degrees, for instance, meant the object was exactly halfway between the horizon and directly overhead. This simple yet powerful interaction, lining up a sight and reading a string, allowed for an incredible range of calculations. It was a handheld calculator that used gravity and geometry instead of batteries and microchips. This seemingly simple device was actually the product of a long and rich intellectual heritage, a fusion of knowledge from different cultures. Its origins can be traced back to the ancient Greek astronomers, but it was scholars in the Islamic world who refined it into its most effective and widespread form. They perfected the geometric projections and trigonometric calculations that made its scales accurate, and they developed the detailed tables of star positions and solar declination that allowed users to interpret their measurements. When this knowledge was translated and spread into medieval Europe, the quadrant was eagerly adopted and adapted. European craftsmen began producing them in great numbers, from large, beautifully made quadrants for fixed observatories to small, pocket-sized versions for travelers. This cross-cultural journey made the quadrant a universal symbol of practical mathematics, a tool as useful in the markets of Damascus as in the monasteries of Oxford. For the medieval mariner, the quadrant was nothing short of revolutionary. Determining a ship's latitude, its north-south position was the navigator's primary concern, and the quadrant provided the key. The method was elegant in its logic. They knew that the height of the North Star, Polaris, above the horizon was almost exactly equal to the observer's latitude. On a clear night, a sailor would simply use the quadrant to measure the angle to Polaris. A reading of 30 degrees meant they were at approximately 30 degrees north latitude. For daytime navigation, they could measure the maximum altitude of the sun at local noon, and by consulting specially prepared tables that accounted for the time of year, convert that solar altitude into their latitude. This ability to find one's position on the trackless ocean was a monumental leap forward, reducing the terrifying uncertainty of sea travel and enabling the longer voyages that would eventually connect the continents. On solid ground, the quadrant's utility was just as profound. Architects and builders used it to calculate the height of structures, a critical skill when designing cathedrals whose soaring spires seemed to touch the heavens. By measuring the angle to the top of a tower from a known distance away, they could use trigonometry to compute its height with impressive accuracy. Surveyors employed quadrants to map land, plot boundaries, and plan irrigation channels, bringing order and organization to the landscape. Even astrologers and physicians used specialized quadrants to cast horoscopes or determine auspicious times for medical procedures, believing celestial angles influenced events on Earth. This incredible versatility, from navigating oceans to raising cathedrals, cements the quadrant's legacy as a foundational instrument. It didn't just measure angles, it built bridges between abstract mathematics and the tangible world, proving that the laws of geometry were not just theoretical concepts but practical tools for shaping human civilization. While the quadrant showcased the power of geometry made portable, the story of ancient instrumentation holds an even more astonishing chapter, one that lay hidden at the bottom of the sea for 2,000 years, waiting to rewrite our understanding of technological history. In the early 20th century, sponge divers exploring a Roman-era shipwreck off the coast of the Greek island of Antikythera made a startling discovery. Amidst the broken pottery and statues, they recovered a heavily corroded lump of bronze, its original form almost unrecognizable. Initially set aside as a curiosity, this object would later be revealed through painstaking analysis as the single most sophisticated mechanical device to survive from the ancient world. Now known as the Antikythera mechanism, it stands as a breathtaking anomaly, a complex, gear-driven astronomical calculator so advanced that nothing remotely comparable would appear again for over a millennium. It was in every sense an ancient analog computer, a device that could predict the future motion of the cosmos with stunning accuracy. Unlocking its secrets required the tools of the modern age. For decades, the mechanism's true complexity remained hidden beneath layers of mineralized crust. It was only with the advent of X-ray and gamma-ray tomography in the 21st century that researchers could peer inside the calcified mass without destroying it. The images that emerged were nothing short of miraculous. They revealed a dense, intricate clockwork of at least 30 interlocking bronze gears, precisely cut with triangular teeth, all housed within a wooden case not much larger than a shoebox. On the front and back were dials, pointers, and inscriptions, forming a sophisticated user interface. This was not a simple navigational aid or timekeeper. It was a mechanical model of the universe designed to simulate the complex and irregular motions of the Sun, the Moon, and the 5 known planets across the sky. By simply turning a hand crank on the side, an operator could advance the mechanism through time, watching as the pointers swept across the dials to display celestial events years or even decades into the future. The mechanism's most dazzling feat was its ability to predict lunar and solar eclipses with remarkable precision, a capability that must have seemed like pure magic to its users. It achieved this through a brilliant understanding of astronomical cycles, particularly the Saros cycle, a period of approximately 18 years and 11 days after which the Sun, Moon, and Earth returned to nearly the same relative positions, causing a similar pattern of eclipses to repeat. The device featured a dial that tracked this cycle, with inscriptions not only predicting the date of an eclipse but also hinting at its characteristics, perhaps indicating the time, direction, and even the color it might appear, which was linked to atmospheric conditions. This wasn't just a calculator, it was an informational display providing a wealth of data for both scientific inquiry and, likely, astrological interpretation. The level of miniaturization and mechanical integration required to achieve this, all crafted by hand, is a feat that continues to humble modern engineers. Though the Antikythera mechanism itself sank beneath the waves around 80 BC, its intellectual legacy did not completely drown. While no medieval instrument matched its complexity, the dream of such a device, a machine that could model the heavens, persisted. Knowledge of geared mechanisms, though rare, was kept alive through texts and oral traditions, particularly in the Byzantine Empire and the Islamic world. Medieval clockmakers, striving to build ever more elaborate astronomical clocks for cathedral towers, were essentially attempting to recreate the Antikythera mechanism on a monumental public scale. These great clocks, with their rotating dials showing the phases of the moon and the positions of the planets, were the spiritual successors to that ancient Greek marvel. They represented a continuous thread of ambition, the human desire to capture the rhythm of the cosmos in the turning of gears, to make the abstract tangible through mechanical genius. The rediscovery of the Antikythera mechanism serves as a powerful and humbling reminder. It shatters the simplistic notion of linear technological progress, proving that peaks of brilliance can emerge, be lost, and then be independently rediscovered centuries later. It tells us that the ancient world was capable of a sophistication we are only now beginning to fully appreciate, and that the medieval scholars who gazed at the stars were not starting from scratch, but were perhaps inspired by fragments of a lost golden age. This one incredible device connects the astronomical speculations of ancient Greece to the geared calculators of the Islamic Golden Age, and finally to the monumental clocks of medieval Europe. It stands as a testament to a forgotten path of technological development, one that measured not just angles or time, but the very cycles of the cosmos itself, inspiring us to next examine how this same understanding of cycles was applied to the powerful and unpredictable force of the ocean's tides. For coastal communities whose lives and livelihoods were intimately tied to the rhythm of the sea, the ability to predict the ocean's ceaseless ebb and flow was not a matter of academic curiosity. It was a vital necessity for survival. The relentless cycle of high and low tides dictated the safest windows for fishermen to launch their boats, for traders to approach harbors without running aground, and for entire villages to harvest the bounty of the exposed seabed. Long before the mathematical formulas of Newtonian physics explained the gravitational pull of the moon and sun, medieval scholars and mariners observed a clear, repeating pattern. The tides followed the moon. They noticed that high tides were higher and low tides were lower during the full and new moons, what we now call spring tides, and that the range was smallest during the quarter moons, the neap tides. This empirical observation of a celestial maritime connection became the foundational principle behind one of the most practical and widely used instruments of the era, the tide calculator. The most common and elegant form this instrument took was the tidal volvelle, a masterpiece of interactive information design crafted from parchment or paper. Often found tucked into the pages of an almanac or a navigational manual, the volvelle was a series of rotating discs, one stacked upon another, each layer representing a different variable in the tidal equation. The largest base disc typically featured a circular calendar marking the days of the lunar month, often adorned with a beautiful illustration of the moon's phases. A smaller top disc, attached at the center with a thread or a cleverly folded paper pivot, was inscribed with the hours of the day and the predicted tidal state for a specific port. By aligning the current moon phase on the lower disc with a reference mark, a user could simply rotate the upper disc to see the predicted times of high and low water for the days ahead. This simple manual operation transformed complex, naturally occurring cycles into a clear, visual schedule, a paper-based computer for planning life around the sea. The creation of these calculators was a remarkable feat of long-term collaborative data collection. Monks in seaside monasteries, with their disciplined daily routines, were often the perfect chroniclers, meticulously recording tidal times and heights alongside their notations of the moon's phase for years, even decades. This accumulated data was then synthesized by scholars, who translated the patterns into the graduated scales of the volvelle. The result was a highly localized tool. A tide calculator made for the port of London would have been useless in Bristol or Calais, as the timing and range of tides vary dramatically with the shape of the coastline and the seafloor. This specificity highlights a sophisticated understanding that natural phenomena, while governed by universal principles, manifest in unique ways within local environments, a cornerstone of modern environmental science. The impact of this instrument on daily life and medieval commerce cannot be overstated. For a fisherman, consulting his tide table could mean the difference between a successful, safe catch and being swept onto treacherous rocks. For a merchant captain, it dictated the precise moment his heavily laden ship could cross a harbor bar to enter port, protecting his valuable cargo and the lives of his crew. This predictive power reduced the terrifying capriciousness of the sea, making maritime travel and trade less a game of chance and more a calculated risk. It empowered coastal societies, giving them a measure of control over a force that had always seemed utterly uncontrollable. The tide calculator stands as a powerful testament to a pre-modern form of science that was deeply pragmatic, rooted in patient observation, and dedicated to harnessing natural knowledge for human benefit. This ingenious application of celestial patterns to earthly challenges perfectly sets the stage for another instrument that also relied on nature's cycles, but to measure a far more personal and universal quantity, the steady, unstoppable flow of time itself. While the tide calculator harnessed the predictable rhythm of the moon to master the sea, another instrument tackled a more constant and universal flow, the steady, unstoppable passage of time itself. Before the reassuring tick of mechanical clocks filled the air, the dominant sound marking the hours in the medieval world was the gentle, rhythmic drip of water. This was the domain of the Klepsidra, or water clock, an invention of breathtaking simplicity and profound impact that transformed a natural element into a reliable measure of human affairs. Unlike the sundial, which fell silent under cloud cover and was useless at night, the Klepsidra worked tirelessly in the dark interiors of monasteries, the bustling halls of justice, and the quiet studies of alchemists, offering a continuous, flowing measure of duration that was independent of the sun and stars. It was the first true step towards a liberated concept of time, one that could be segmented and managed regardless of the weather or the time of day. The fundamental principle was elegantly straightforward. Time was measured by the regulated flow of water from one container to another. The simplest form involved a bowl or a jar with a small hole drilled near its base. As water steadily trickled out, the dropping water level past a series of internal markings would indicate the passage of hours or smaller units. This basic design, however, was just the starting point. Medieval ingenuity, particularly in the Islamic world and China, elevated the water clock into a marvel of hydro-mechanical engineering. To maintain a constant flow rate, the key to accuracy, engineers devised clever solutions. The most common was a three-container system. An upper reservoir supplied a constant head of water to the central measurement vessel, ensuring the pressure, and thus the flow speed from its outlet, remained steady throughout its operation. This attention to hydraulic precision turned a simple dripping bowl into a truly reliable timekeeping instrument. But the true wonder of these devices lay in their transformation of pure utility into public spectacle and artistic expression. The most magnificent water clocks were monumental automata, designed not just to tell time but to announce it, celebrate it, and make its abstract nature vividly tangible. In the court of the Holy Roman Emperor Charlemagne, a gifted craftsman presented a water clock so elaborate it caused a sensation. As each hour passed, little bronze horsemen would emerge from behind tiny doors to parade around the clock face, while mechanical birds chirped and small cymbals clashed. In the great cities of the medieval Islamic world, like Damascus and Baghdad, enormous public water clocks adorned with intricate gearwork would ring bells, cause figurines to move, and even drop metal balls into gongs to mark the hours for the entire city to hear. These were more than timekeepers. They were the centerpieces of civic pride, breathtaking demonstrations of a ruler's wealth and a society's technical prowess, blending the skills of the blacksmith, the carpenter, and the artist into a single, mesmerizing machine. Their practical application, however, was what cemented their place in daily life. In medieval monasteries, the Klepsidra was the unseen regulator of the divine office, the canonical hours of prayer that structured a monk's entire existence. A designated brother would watch over the water clock, ensuring the community was summoned for matins, lauds, and vespers at the correct times throughout the day and night, maintaining a sacred rhythm that was utterly divorced from the natural cycle of light and dark. In courtrooms across Europe, the water clock was the impartial arbiter of justice, used to meter the speaking time allotted to plaintiffs and defendants, ensuring fair hearings and giving us the modern phrase, to have the floor. For early scientists and alchemists, the steady drip of the Klepsidra provided the first accurate means of timing experiments, allowing them to observe and record changes that occurred over precise intervals, a foundational practice for the emerging scientific method. The legacy of the water clock flows directly into the heart of the modern world. The mechanical principles developed to control the flow of water, the gears, escapements, and feedback systems that governed the automata, provided the essential blueprint for the first weight-driven mechanical clocks. The very idea of segmenting the day into equal, measurable hours, a concept refined by the continuous operation of the Klepsidra, fundamentally changed how society organized itself, paving the way for the timed schedules of work, commerce, and transportation we live by today. The water clock taught humanity that time was a river that could be channeled, measured, and put to use, an insight that shifted our relationship with the universe from one of passive observation to active management. This mastery of an elemental force to impose order introduces a tool that sought to bring that same order to another invisible, powerful element, the capricious and ever-changing wind. Amidst the vast and featureless expanse of the open ocean, where the sea and sky merge into a disorienting sameness, medieval navigators clung to a single, beautifully crafted diagram as their lifeline to direction and destination. This was the wind rose, a stunning fusion of art, myth, and empirical observation that transformed a blank parchment into a guide to the very winds themselves. Originating in the Mediterranean, the earliest wind roses were simple circles divided by lines indicating the 8 principal winds, each with its own name and personality derived from ancient Greek and Roman lore. The Tramontana blew cold from the north, the Sirocco carried dust from the Sahara, and the warm Austro arrived from the south. These were not abstract directions. To a sailor, they were distinct forces, each with its own character and influence on a voyage. Chart makers began embellishing these diagrams, turning the end points of the wind lines into elaborate artistic flourishes, fleur-de-lis for north, ornate crosses for east, and often the faces of cherubs or bearded gods puffing their cheeks to blow ships across the waves. This wasn't mere decoration, it was a functional memory aid, a visual language that allowed an illiterate sailor to instantly understand and communicate the capricious moods of the atmosphere. The true revolution, however, began when this artistic wind diagram collided with a groundbreaking technological discovery: the magnetic properties of lodestone. Chinese navigators had known for centuries that a sliver of this naturally magnetic mineral, when floated on water or suspended from a thread, would consistently align itself with the north-south axis of the Earth. As this knowledge traveled west along trade routes, European and Arab instrument makers had a brilliant insight. They merged the pragmatic, pointing needle with the beautiful, directional wind rose, creating the instrument we now know as the compass. The floating needle was placed at the very center of the wind rose diagram, which was now redrawn with the cardinal points north, east, south, west clearly emphasized. This transformed the rose from a representation of the wind's direction into a reliable indicator of the ship's direction. The diagram was no longer just a map legend. It became a functioning instrument dial, a compass rose that turned with the vessel, its north point faithfully following the lead of the magnetic needle hidden beneath it. This fusion of empirical science and elegant design was one of the most consequential in history, turning abstract magnetism into a steerable course. This new magnetic compass rose didn't just guide ships, it fundamentally reshaped the art of mapmaking and the very conception of the world. Prior to its widespread adoption, Portolan charts, the detailed sailing maps of the Mediterranean, were often oriented with east at the top, reflecting religious and traditional cosmographies. But the compass insisted on magnetic north. As a result, mapmakers began to standardize their charts with north at the top, a convention born from the utility of the instrument that we still follow universally today. The rose became the central focal point of these charts, with lines radiating from it across the parchment like the spokes of a wheel. These room lines provided sailors with a constant reference grid. By aligning the compass rose on their physical compass with the one on the map, they could plot a straight-line course from one port to another, simply by keeping their vessel at a constant angle to the north-south axis indicated by the needle. This system of loxodromic navigation, while not always the shortest great circle route, provided something priceless: predictability and confidence. A captain could now trace a line on a map and know that by holding a steady course, he would eventually reach his goal. The cultural and economic impact of this humble diagram was nothing short of monumental. With a compass rose to guide them, navigators could venture beyond the cautious practice of cabotage, hugging the coastline from one familiar headland to the next, and strike out across open water. This opened up the world. It enabled the lucrative direct trade routes across the Mediterranean and later, the terrifying but profitable voyages down the coast of Africa and across the Atlantic Ocean. The compass rose was the silent partner on the voyages of Diaz, da Gama, and Columbus, a tool that made the age of discovery possible by reducing the overwhelming fear of the unknown. It turned the trackless sea into a structured grid of possibilities, encouraging the exchange of not just goods, but ideas, technologies, and cultures between continents that had been isolated for millennia. This powerful tool for visualizing and navigating the terrestrial world beautifully sets the stage for a device that applied the same principles of diagrammatic clarity to the far more vast and distant celestial sphere. While the compass rose masterfully charted a course across the two-dimensional surface of the sea, the night sky presented a far grander and more complex challenge, a dome of stars that rotated overhead in a nightly spectacle. For a medieval scholar or traveler, memorizing every constellation and its seasonal dance was a formidable task. The solution to translating this celestial sphere into a manageable, portable format was the Planisphere, a deceptively simple disk that acted as a customizable window to the universe. Unlike the Astrolabe with its intricate gears or the Armillary sphere with its imposing rings, the Planisphere's genius was in its elegant flatness. It was, in essence, a star chart that could be dialed to match any night of the year, transforming a fixed map into a dynamic tool that put the rhythm of the cosmos directly into the user's hands. Its operation was a beautiful lesson in projection. The challenge was to accurately represent the curved, dome-like vault of the sky onto a flat, two-dimensional surface. Medieval craftsmen achieved this using a polar azimuthal projection. Imagine the entire night sky pivoting around the North Star, Polaris. The Planisphere captured this view by placing Polaris at the very center of the disk. The stars surrounding it were then carefully plotted outward, with their positions distorted in a precise, mathematical way to fit the flat plane, much like a modern world map flattens the globe. This central disk, containing all the visible stars for a given latitude, was then overlain by a second disk, the mask. This top layer had an oval-shaped window cut out of it, representing the portion of the sky visible above the horizon at any one time. The real magic happened when the user rotated this mask. The window would reveal different sets of stars, perfectly mimicking how the real night sky changes not only throughout a single night but across all the months of the year. Creating an accurate planisphere was a deeply personalized process, because the portion of the sky visible from Earth depends entirely on one's latitude. A planisphere made for a stargazer in London would be utterly useless for someone in Alexandria or Baghdad. The star patterns near the horizon would be completely different. Therefore, each instrument had to be painstakingly calculated and crafted for a specific band of latitude. This meant a scholar would often commission a planisphere as a bespoke tool, a personal companion for their astronomical pursuits. They were crafted from durable parchment, vellum, or even thin sheets of brass or pewter for wealthier patrons. The stars themselves were often depicted as tiny, punched holes or as delicate points of ink, sometimes with faint lines connecting them to outline the mythical figures of the constellations. This careful customization made the planisphere incredibly accurate for its intended location, a portable planetarium that could be slipped into a pouch and consulted anywhere, from a lonely hilltop to the deck of a gently rocking ship. For the medieval user, the planisphere was less a calculator and more a visual guide and planning aid. A monk could use it to determine which constellations would be visible for his nighttime prayers or to anticipate the arrival of a seasonally significant star. A traveler could familiarize himself with the night sky of a foreign land before even setting foot there, reducing the disorientation of a new horizon. Its primary function was educational and preparatory. It allowed someone to learn the sky without having to spend countless cold nights making mistakes. By turning the dial to a future date, one could plan an observation session, knowing exactly when a particular planet might rise or when a favorite constellation would be high in the sky. This ability to simulate the passage of time and predict celestial events democratized astronomical knowledge, making it accessible to students and enthusiasts who lacked the advanced mathematical training required to operate an astrolabe or interpret complex tables. The legacy of the planisphere is beautifully visible in any modern astronomy magazine or app. The classic star wheel or rotating star finder given to amateur stargazers today is a direct descendant of the medieval planisphere, operating on the exact same principle of a rotating mask over a fixed star chart. This enduring design, largely unchanged for centuries, is a powerful testament to its effectiveness. It represents a pivotal moment in the history of science, the shift from astronomy as a purely scholarly, calculation-driven pursuit to a more accessible, observation-based hobby. The planisphere invited anyone with curiosity to look up and engage with the universe directly, using a tool that was both simple to understand and profoundly deep in its application. This act of bringing the heavens down to a human scale, of making the cosmic intimately personal, paves the way for a tool that performed a similar feat of simplification and precision, but for a far more terrestrial and grounded purpose, the fundamental task of measuring and dividing the land itself. After mapping the heavens with the Planisphere, we turn our attention back to Earth, to the very dirt beneath our feet and the profound human need to measure, divide, and impose order upon the land. The grand Roman roads that stretched for thousands of miles in near-perfect straight lines, the majestic aqueducts that marched across valleys on towering, level arches, the precisely laid-out grids of military camps and new cities, these were not acts of guesswork. They were the product of meticulous engineering made possible by a deceptively simple tool that masterfully harnessed the most fundamental force of nature, gravity. This was the Groma, a device that turned the abstract principles of geometry into physical reality, ensuring that the ancient and medieval worlds were built on lines that were truly straight and angles that were perfectly square. At its heart, the Groma was an instrument of beautiful simplicity, a testament to the idea that the most powerful tools are often the most straightforward. Imagine a vertical staff planted firmly into the ground. At its top sat a horizontal cross, typically crafted from wood or bronze, with each of its 4 arms forming a perfect right angle. From the end of each arm, a plumb bob, a simple weight on the end of a string, hung down, using the unwavering pull of gravity to establish a true vertical reference. The surveyor, known as an agrimensor or land measurer, would sight along pairs of these hanging lines to establish straight lines and, most importantly, perfect right angles over vast distances. By carefully aligning one set of plumb lines with a distant marker, he could then pivot the entire device and use the perpendicular set of lines to sight a new line exactly 90 degrees from the first. This elegant application of basic physics provided the foundational grid upon which empires were literally built. The impact of this humble tool on the Roman landscape and later on medieval infrastructure is almost impossible to overstate. It was the essential instrument for centuriation, the process of dividing conquered territories into square plots for veteran soldiers and for agricultural use. This created the characteristic checkerboard patterns of farmland that can still be seen from the air in parts of Europe today, a lasting imprint of Roman organization etched into the very soil. When laying out a new road, teams would use the Groma to sight a straight line toward a distant high point, such as a hill or a mountain. Laborers would then clear the path ahead, and the surveyors would move forward to set up the Groma again, repeating the process mile after mile, resulting in the arrow-straight highways that were the backbone of Roman military and economic power. For constructing aqueducts, which required an incredibly gentle, consistent slope over many miles to keep water flowing, the Groma was used in conjunction with water levels to ensure that the gradient never deviated, a feat of precision engineering that still inspires awe. What is perhaps most remarkable about the Groma is its incredible longevity and reliability. Unlike more complex geared devices, the Groma had no moving parts to wear out or delicate mechanisms to fall out of calibration. Its accuracy depended solely on the unchanging laws of physics. Gravity always pulls straight down. This made it incredibly durable and easy to use, even for soldiers or workers with limited formal training. A Groma could be packed down and transported easily, then quickly reassembled on any new frontier. This combination of ruggedness, simplicity, and perfect accuracy ensured that its design remained essentially unchanged for over a millennium. Long after the fall of Rome, medieval engineers and monastic communities continued to use the Groma for laying out property boundaries, planning new towns, and constructing castles and cathedrals, preserving a vital thread of practical geometric knowledge through the centuries. The Groma's legacy is the physical world around us. It represents the translation of abstract mathematical perfection, the concepts of the straight line and the right angle, into the tangible reality of our built environment. It was a tool that didn't just measure the world as it was, but was used to create a new, more ordered world according to human design. The grid plans of our modern cities, the straight lines of our property boundaries, and the precise alignments of our foundational infrastructure all owe a silent debt to this ancient surveying cross. It proved that order could be imposed upon chaos with little more than a wooden cross, some string, and a few weights, demonstrating that the most profound engineering often begins with the simplest of principles. This mastery of physical space and geometric harmony finds a fascinating parallel in the next instrument we will explore, which sought to measure a far more ethereal and intangible form of harmony, the mathematical ratios that create beautiful music. Yet after mastering the geometry of land and stone, the medieval mind turned its attention to a far more elusive dimension of reality, the invisible world of sound and vibration. This quest for understanding the hidden structures of harmony led to one of the most elegantly simple and profoundly influential instruments ever created, the monochord. Picture a long, narrow wooden box, atop which a single gut string is stretched taut between two fixed bridges. A third, movable bridge could be slid carefully beneath the string, dividing it into two segments of precise, adjustable length. When plucked, the string would hum, its pitch shifting from a deep, resonant tone to a higher, sharper note as the bridge was moved, transforming an abstract mathematical ratio into a tangible, audible experience. This was not an instrument for performance, but for revelation. A laboratory in miniature dedicated to uncovering the secret mathematical language that was believed to govern everything from music to the motion of the planets. The true power of the monochord lay in its ability to make the invisible laws of acoustics not just audible, but measurable. A medieval scholar like Anicius Manlius Severinus Boethius, whose writings became foundational to medieval music theory, would use the device to demonstrate that musical consonance was not a matter of subjective taste, but of mathematical perfection. He would show that when the movable bridge divided the string into two equal halves, the two resulting pitches were identical an octave, and the ratio was the simple and perfect 1:2. Slide the bridge to divide the string in a 3:2 ratio, and the resulting interval would ring out as a harmonious fifth. A 4:3 ratio produced a clear, stable fourth. These were the perfect consonances, and their corresponding ratios were small, whole numbers. Dissonant intervals, by contrast, were created by complex, messy ratios that the ear naturally rejected. This was a staggering discovery. Beauty and ugliness in sound were not arbitrary. They were the direct products of mathematical order, a physical law that could be seen, heard, and proven with a piece of wood and a single string. This discovery resonated far beyond the music room, echoing into the highest realms of medieval philosophy and cosmology. Inspired by ancient Greek thinkers like Pythagoras, scholars came to believe that these same simple ratios that governed musical harmony must also govern the architecture of the cosmos itself. This was the magnificent concept of the harmony of the spheres, the idea that the planets, as they moved through their celestial orbits, generated a sublime, inaudible music through the mathematical perfection of their speeds and distances. The monochord was the physical proof of this philosophy. By generating perfect intervals, it was not just making music, it was replicating on a small, human scale the very same divine mathematics that moved the heavens. The instrument became a bridge between the earthly and the celestial, a tool that allowed a philosopher to argue that the entire universe was constructed like a vast, cosmic monochord, its strings vibrating in proportions that created the perfect, eternal music of creation. In the practical world of medieval education, the monochord was an indispensable teaching tool, the foundation of the quadrivium, the four advanced liberal arts of arithmetic, geometry, music, and astronomy. Before a student could even think of touching a complex polyphonic composition, they had to first master the pure intervals on the monochord, training their ear to recognize the sound of mathematical truth. It was the standard against which all other instruments were tuned, and the reference point for understanding the modes and scales used in both sacred chant and secular song. This rigorous grounding in acoustic mathematics ensured that every trained musician was also something of a mathematician and a natural philosopher, their art deeply informed by a scientific understanding of its underlying principles. The monochord, in essence, wove the threads of art and science into a single, inseparable tapestry, demonstrating that to truly understand music, one had to understand number, and to comprehend number, one could listen to music. The legacy of this simple device is both vast and subtle. Its principles directly influenced the design of every stringed instrument that followed, from the lute to the violin, ensuring their fret placements and tuning systems were based on acoustic truth rather than guesswork. More profoundly, it established a worldview that saw the universe as an orderly, rational, and mathematically intelligible place, a key precondition for the later scientific revolution. The monochord taught that beneath the apparent chaos of the sensory world lay a hidden structure of elegant numerical relationships, waiting to be discovered by those with the right tools. This conviction that nature could be understood through measurement and ratio, first proven with a vibrating string, would eventually be applied to light, motion, and force, setting the stage for every instrument of discovery that followed. From the precise mathematical harmonies of the monochord, we now venture into a realm where medieval innovation embraced the tangible, the volatile, and the transformative. In the dim, fire-lit workshops of alchemists and apothecaries, a different kind of instrument reigned, one designed not to measure angles or sound, but to manipulate matter itself. This was the Alembic, a sophisticated assembly of glass vessels that turned the art of distillation into a powerful engine of discovery. At first glance, it might seem a world apart from the astronomical tools we've explored, but it shared the same core ambition: to uncover the hidden principles governing nature. While one looked to the stars, the Alembic looked into the very essence of substances, seeking to purify, separate, and ultimately understand the building blocks of the material world through a process of controlled transformation. The apparatus itself was a masterpiece of functional glassblowing, a testament to the medieval artisan's skill. Its name comes from the Arabic al-anbic, itself derived from the Greek ambics, meaning cup or beaker. A typical setup consisted of three main parts. First, the cucurbit, a large, rounded flask that served as the boiling vessel where the raw material, be it wine, herbs, or minerals, was heated. This was capped by the alembic proper, a dome-shaped head that fit snugly over the cucurbit, featuring a long, downward-sloping spout. As the heated vapors rose from the boiling mixture, they would condense on the cool inner surface of this dome and trickle down into the spout. Finally, the spout would channel these precious droplets into a third vessel, the receiver, where the purified distillate was collected. This elegant, continuous cycle of evaporation and condensation was a physical process made visible, a miniature water cycle playing out on a workbench. Though its origins are ancient, the design was perfected and its applications vastly expanded by medieval scholars, particularly in the Islamic world. Figures like Jabir ibn Hayyan and later European alchemists such as Ramon Llull saw the alembic not just as a tool, but as a philosophical instrument. They believed that through distillation, one could separate the pure spirit or essence of a substance from its coarse, earthly body. This was more than chemistry. It was a spiritual metaphor made manifest in glass. In their quest to transmute base metals into gold or discover the elixir of life, These practitioners meticulously recorded their results, noting temperatures, times, and the properties of the strange new liquids they created. This rigorous, if often secretive, documentation of experimental procedures established a foundational methodology for empirical science, built upon observation, repetition, and the meticulous use of specialized tools. The impact of this work, however, extended far beyond the elusive dream of transmutation. The real legacy of the Alembic is found in profound practical advancements that touched everyday life. In pharmacology, apothecaries used distillation to isolate the active medicinal compounds from plants, creating potent essential oils, tinctures, and cordials that were far more effective than simple herbal preparations. The production of strong alcoholic spirits, literally named aqua vitae or water of life, was a direct result of alembic technology, with applications ranging from antiseptics to anesthetics. In metallurgy, alchemists used similar principles to distill and purify acids like nitric acid and aqua regia, which were crucial for assaying metals and etching designs. This relentless experimentation, driven by the Alembic, slowly built a vast, hands-on knowledge of chemical reactions and material properties that would later form the bedrock of modern chemistry. The Alembic, therefore, stands as a powerful symbol of the medieval hands-on approach to knowledge. It represents a shift from purely theoretical speculation to active, experimental interrogation of nature. Each distillation was a question asked of a substance, and the resulting liquid was its answer. This process of trial and error, of carefully observing the outcomes of a controlled process, is the very heart of the scientific method. The Alembic was a tool that facilitated discovery by doing, proving that understanding could be boiled, vaporized, and condensed from the physical world itself. This relentless pursuit of material transformation through applied heat and ingenious design beautifully sets the stage for an instrument that measured a far more subtle and pervasive transformation, the invisible yet palpable changes occurring within the atmosphere itself. While alchemists used the Alembic to transform liquids through applied heat, another instrument was designed to read the invisible messages carried by the air itself. This was the weather glass, a humble yet revolutionary device that allowed medieval observers to literally see changes in the atmosphere's weight, providing one of the first tangible links between air pressure and impending weather. Imagine a simple glass bottle, its neck elegantly elongated and bent into a graceful spout that dipped down into a small reservoir of water. The body of the bottle was left partially filled with water, leaving a pocket of air trapped inside. This entire assembly was often mounted on a wooden stand, sometimes adorned with carved figures or painted scales, transforming a basic scientific principle into a functional piece of art for the home or workshop. Its operation was a silent, continuous performance. As the atmospheric pressure outside the bottle changed, it would push down on the surface of the water in the reservoir, forcing the liquid level inside the spout to rise or fall in a delicate, responsive dance. A rising column of water in the spout indicated increasing pressure, often heralding fair, stable weather, while a sudden drop suggested falling pressure and the approach of storm clouds and rain. This seemingly simple apparatus represented a monumental shift in humanity's relationship with the environment. For centuries, weather prediction had been the domain of folklore, superstition, and astrological guesswork. A farmer might note the aching in his knee or the behavior of livestock as signs of an approaching storm. The weather glass introduced something entirely new, an empirical, instrument-based method for forecasting. It didn't rely on omens or traditions. It responded directly to a physical force, the weight of the air itself. This was a profound leap toward a scientific understanding of meteorology, suggesting that the weather was not a capricious act of the gods but a complex system governed by measurable natural laws. By carefully observing and recording the correlation between the water level in the spout and the weather that followed, users could build a practical, localized understanding of how atmospheric changes manifested in wind and precipitation. A sailor might note that a rapid drop in the glass often preceded a squall, giving him precious time to reef the sails, while a farmer could use a steady high reading to confidently plan for several days of drying hay. The development and refinement of the weather glass were deeply intertwined with the era's growing curiosity about the physical properties of air and the concept of a vacuum. Medieval natural philosophers were grappling with the idea that air had substance and weight, contradicting the ancient Aristotelian belief that nature abhorred a vacuum. The weather glass, in its simplest form, was a powerful demonstration of atmospheric pressure in action. It proved that the air pushing down on the open reservoir could support a column of water inside the sealed spout, a principle that would later be quantified by Evangelista Torricelli in the invention of the mercury barometer in the 17th century. In this way, the crude medieval weather glass was a direct intellectual forerunner to the precise instruments of modern meteorology. It paved the way for the network of barometric stations that now provide the data for our daily forecasts, representing the first tentative step toward understanding the dynamics of high and low pressure systems that govern our weather. Beyond its scientific importance, the weather glass held a cherished place in daily medieval life, particularly for those whose livelihoods depended on the whims of the sky. It became an essential fixture in the great halls of manor houses, where the lord of the estate would consult it alongside the steward to plan the week's agricultural activities. In coastal villages, it was a common sight in taverns and guild halls, where fishermen and merchants would gather to debate its readings before venturing out to sea. Its accessibility was key. Unlike the complex Astrolabe or the expensive Armillary sphere, the weather glass could be understood by anyone. It required no knowledge of mathematics or astronomy to interpret it, just a willingness to observe and learn from its silent, liquid signals. This democratization of weather prediction empowered communities, giving them a practical tool to manage risk and make informed decisions, reducing the paralyzing fear of the unknown that so often accompanied changes in the weather. Its role as a trusted advisor in matters of commerce and survival creates a natural bridge to the next frontier of measurement, one that turned its focus inward, from the vastness of the atmosphere to the intimate rhythm of the human body. This meticulous attention to the body's internal rhythms marked a profound expansion of instrumentation's reach, moving its precise gaze from the vastness of the cosmos to the intimate, pulsing reality of human biology. Where astronomers tracked the grand cycles of planets and stars, physicians now sought to map the microcosm of the human body, using timekeeping technology to quantify health and diagnose imbalance. The primary tool for this new science was the pulse watch, a specialized instrument born from the urgent need to measure life's most fundamental metric, the rhythm of the heart itself. Before the invention of the stopwatch or even the widespread use of pendulum clocks, medieval doctors relied on a fascinating array of devices to count these vital beats, from finely crafted miniature sunglasses that measured short intervals to early mechanical clocks with special second beating mechanisms. This wasn't merely about counting, it was about listening to the body's own music and deciphering its tempo, a practice that wove together ancient wisdom and emerging empirical science into a more systematic approach to healing. The art of pulse reading, or sphygmology, had ancient roots stretching back to the teachings of Galen in the Roman era, and even earlier to physicians in China and India. These traditions describe dozens of different pulse qualities: quick or slow, strong or weak, regular or irregular, each believed to correspond to specific conditions, humoral imbalances, and even emotional states. The medieval physician inherited this complex symbolic language, but they faced a significant practical challenge: how to objectively measure and compare these rhythms. Relying on subjective perception alone, perhaps by humming a tune or silently counting, was too imprecise for making reliable diagnoses or tracking a patient's progress over time. The solution was to bring the newly refined concept of standardized time into the diagnostic process, by using a sandglass that emptied in exactly 1 minute, or by observing the movement of a clock's hand. A doctor could count the number of pulses within a fixed interval, transforming a qualitative impression into a quantitative data point. This simple act of measurement was a quiet revolution, introducing numerical objectivity into a field long dominated by subjective interpretation and tradition. The instruments themselves were often beautiful hybrids of form and function. Apothecaries and physicians might commission special sandglasses, known as pulsilia, which were smaller and more delicate than their nautical counterparts, often crafted from fine blown glass with ornate wooden or ivory frames. These would be designed to measure a medical minute, a standardized interval perfect for counting a resting pulse. As mechanical clocks became more advanced, some were built specifically for medical use, featuring a prominent seconds hand or an audible tick that beat at a precise interval, allowing the physician to auscultate without taking their eyes off the patient. This marriage of timekeeping and medicine required the doctor to become a master of divided attention, feeling the thready beat at a patient's wrist while simultaneously watching the sand fall or the hand move, a skill that demanded intense concentration and a deep understanding of rhythmic patterns. The resulting pulse rate became a crucial piece of diagnostic evidence, a number that could be recorded in a ledger and compared from one visit to the next, bringing a new level of systematic record-keeping to patient care. This practice perfectly illustrates the unique blend of tradition and innovation that characterized medieval medicine. The underlying theory was often still deeply rooted in Galenic humoral principles. A fast, bounding pulse might indicate an excess of blood and a state of inflammation, while a slow, weak pulse could suggest a melancholic disposition. However, the method of assessment was becoming increasingly empirical and technical. The pulse watch provided a common reference point that could be communicated between practitioners, making medical knowledge less esoteric and more shareable. It represented a shift towards a more evidence-based practice, where treatment decisions could be informed by measurable changes in the patient's condition. This interdisciplinary approach, pulling technology from clockmakers and applying it to biological observation, showcases a burgeoning scientific mindset that sought to understand the human body with the same rigorous tools used to understand the natural world. This newfound fascination with measuring precise intervals of time within the body creates a natural and fascinating link to a completely different, yet strangely parallel field of endeavor: the quest to impose that same temporal precision onto the art of music. Having mastered the art of measuring the rhythm of the human pulse, this same drive for temporal precision found a powerful and beautiful expression in the world of art. For medieval musicians, particularly those performing in the vast, resonant spaces of cathedrals or in large secular ensembles, a formidable challenge emerged: how to start together, stay together, and end together when dozens of voices and instruments were involved. The solution was not found in a conductor's waving baton, as we know it today, but in a series of ingenious mechanical devices that became the precursors to the modern metronome. These were not mere timekeepers. They were the silent, pulse-giving heart of a musical performance, ensuring that the complex polyphonic masses and intricate motets of the era unfolded with the disciplined rhythm believed to reflect the divine order of the cosmos itself. The most common and accessible of these devices was the pendulum, employed in a form far simpler than Galileo's later experiments. A choir master or a designated time beater might use a length of string with a weight at its end, setting it swinging at the beginning of a piece. The steady, predictable arc of this pendulum provided a visual metronome for the musicians, its period determined by the length of the string. By observing this silent, swinging guide, singers could maintain a consistent tempo, preventing the music from rushing in exciting passages or dragging during more solemn moments. For more portability, some musicians used a tall, vertical staff with a sliding weight. By moving the weight up or down the staff, they could shorten or lengthen the pendulum's effective length, thereby adjusting the tempo to suit the specific piece being performed. This simple tool translated the abstract concept of musical speed into a visible, physical motion, a shared reference that kept an entire ensemble perfectly synchronized. For situations requiring a more autonomous and audible timekeeper, medieval ingenuity turned to a trusted technology, water. Adapted from the principles of the Klepsidra, water-based musical clocks provided a continuous, audible pulse. One design involved a closed container that slowly filled with water. Once a certain level was reached, the vessel would tip over, striking a bell or a gong before righting itself to begin the cycle again. The rate of this pulse could be finely adjusted by controlling the flow of water into the vessel, allowing for a customizable tempo. Another design used a water wheel mechanism that would advance one tooth at a time at a fixed rate, each movement producing a soft click or tap. These devices were particularly valuable during lengthy liturgical services, where fatigue could easily cause the tempo to waver over hours of continuous chanting and singing. The unwavering mechanical pulse ensured that the sacred music maintained its solemn, meditative pace from the first hymn to the final Amen, its rhythm as constant and reliable as the divine order it celebrated. The development of these tools had a profound and lasting impact on music itself, pushing the art form toward greater complexity and sophistication. Before their use, musical notation primarily indicated pitch, with rhythm being a more fluid element, often passed down through oral tradition and conducted with vague hand gestures. The need to synchronize with a mechanical timekeeper necessitated a more precise way of writing down rhythm. This drive led to the refinement of mensural notation in the 13th and 14th centuries, a system that used different note shapes to clearly indicate their duration relative to one another. A longa was worth 2 breves, a breve was worth 2 semibreves, and so on. This was a revolutionary shift, akin to developing a standardized musical language that could be accurately read and reproduced by any trained musician anywhere in Europe. The mechanical pulse of the precursor metronome had directly fostered the creation of a mathematical framework for rhythm, codifying time itself onto the parchment staff and enabling the composition of the incredibly complex polyphonic works that define the late medieval period. This fascinating intersection, where the mechanical necessity of keeping time catalyzed a new language of artistic expression, perfectly illustrates the symbiotic relationship between technology and art in the medieval world. The musician's creative desire for complex, synchronized sound drove the technologist to refine ever better timekeeping devices. In turn, those devices empowered composers to write music of previously impossible rhythmic intricacy, which then again demanded even more precision from performers. It was a virtuous cycle of innovation, proving that the pursuit of beauty can be one of the most powerful engines for practical invention. This mastery of measured flow, of channeling a natural force like gravity into a controlled, predictable rhythm, creates a natural conceptual bridge to the next class of instruments, which applied a very similar principle of measurement to a far more powerful and elemental force, the unstoppable flow of water through the landscapes they sought to tame. From the measured tempo of music and the rhythm of the human pulse, we now turn to an instrument that quantified one of the most powerful and essential forces in the medieval world, the relentless flow of water itself. For communities whose survival and prosperity were inextricably linked to rivers and streams, simply knowing the depth of a waterway was not enough. To truly harness its power for mills or to manage its bounty for irrigation, they needed to understand its speed and volume. This required moving beyond simple observation to precise measurement, a challenge that led to the development of the current meter, a tool that brought mathematical order to the seemingly chaotic movement of water, optimizing the engines of medieval industry and agriculture. The most common and elegantly simple design involved a calibrated float, a device that transformed a humble piece of wood into a precise scientific instrument. A craftsman would carefully weight and shape a buoyant object so that a specific portion of it remained above the surface while the rest sat submerged at a constant depth. This float would then be released into the current and its speed measured over a known distance. The simplest method used a marked rope and a sandglass. An observer would time how many seconds it took for the float to travel between two stakes driven into the riverbank. By calculating the distance traveled per unit of time, they could determine the surface velocity of the water. For more accurate readings, some designs employed a double float system, with a small, weighted subsurface float attached by a line to a larger surface marker. This configuration helped mitigate the distorting effect of surface winds and provided a better average of the water's speed throughout its profile, yielding a more reliable figure for the total volume flowing past a point each second. This data was absolutely critical for the economic life of a medieval village or manor. The most direct application was in the construction and operation of watermills, the powerhouse of the pre-industrial world. A millwright tasked with building a new grain mill couldn't rely on guesswork. He needed to know the river's flow rate to correctly size the mill race, the channel that directed water to the wheel, and to design the wheel itself. A wheel built for a powerful, fast-flowing stream would be inefficient and potentially dangerous on a slower, more placid river, and vice versa. By using a current meter, the millwright could calculate the available hydraulic power and build a wheel that extracted the maximum amount of energy, ensuring the mill could grind more grain, saw more wood, or full more cloth, directly contributing to the wealth and sustenance of the entire community. The same principles were vital for managing the lifeblood of agriculture, irrigation. In arid regions or during summer droughts, water was a scarce commodity that had to be allocated fairly and efficiently among farmers. The current meter provided the data needed for this careful management. By measuring the flow rate in a main irrigation channel, a watermaster could determine how much water was available for distribution. He could then calculate how long to open the sluice gates feeding each farmer's field to deliver a specific, agreed-upon volume, ensuring that those downstream received their fair share after those upstream had taken theirs. This wasn't just about efficiency, it was about preventing conflicts and fostering cooperation, using measured data to manage a precious shared resource. This application of the current meter highlights a sophisticated understanding of practical hydrology, demonstrating that medieval innovation was often driven by the most fundamental human needs: food, power, and social harmony. While the current meter masterfully quantified the raw power of flowing water, another instrument sought to capture a far more subtle and elusive quality: the illusion of depth on a flat surface. For the medieval artist or architect, representing the three-dimensional world with convincing realism was one of the most daunting technical challenges imaginable. The human eye naturally sees in perspective parallel lines appear to converge in the distance, and objects shrink as they recede, but translating this optical truth onto parchment or a wooden panel required a method beyond mere skilled draftsmanship. The solution emerged not from a sudden burst of artistic genius, but from the careful application of mechanical aids, the most ingenious of which was the perspectograph. This family of devices employed a simple yet profound principle, that any complex form, when viewed through a structured grid, could be broken down into manageable, measurable parts and faithfully reproduced. One of the most common and accessible forms of the perspectograph was the simple grid of strings. An artist would construct a physical frame, often made of wood, across which a network of fine threads would be stretched at regular intervals, creating a transparent grid of identical squares. This frame would be positioned between the artist's eye and the subject they wished to draw, be it a living model, a bustling cityscape, or a complex architectural detail. On their drawing surface, a sheet of parchment or paper, they would lightly sketch a corresponding grid of the same number of squares. The magic happened square by square. Instead of being overwhelmed by the entire scene, the artist would focus only on the lines and shapes contained within a single compartment of the live grid, and then meticulously transfer those same relationships into the corresponding square on their paper. This process of reduction transformed the act of drawing from an exercise in holistic interpretation into a series of discrete, solvable geometric problems, ensuring that the proportions and angles of the original subject were captured with astonishing accuracy. For architectural draftsmen and master builders whose plans would determine the stability and beauty of a soaring cathedral or a fortified castle, a different type of perspectograph was essential. They often used a sighting device, sometimes called a clerestory, which functioned like a primitive theodolite. This instrument might consist of a fixed viewpoint and a movable sighting rule or a taut string. By aligning the sight with specific points on a building or a landscape, the draftsman could precisely measure angles and record sight lines directly onto his plan. This allowed for the creation of scaled drawings that accurately represented how a structure would look from a specific vantage point, a crucial tool for presenting designs to patrons and for ensuring that the various teams of stonemasons and carpenters were all working from the same visual understanding. These detailed plans, often preserved in magnificent medieval sketchbooks, reveal a level of pre-construction planning and geometric sophistication that completely dispels the myth of the Dark Ages as a time of crude building. The impact of these tools on the course of art cannot be overstated. While the full mathematical laws of linear perspective were famously codified by Filippo Brunelleschi and Leon Battista Alberti in the early Renaissance, their groundbreaking work did not emerge from a vacuum. It was built upon a solid century of experimentation by medieval artists who were already using devices like the perspectograph to achieve increasingly convincing illusions of depth. The tool acted as a bridge between intuitive approximation and scientific certainty. By relying on a mechanical grid, artists trained their eyes to see the world in a new way, to understand it as a series of spatial relationships that could be measured and calculated. This practice slowly baked the principles of perspective into the artistic consciousness, preparing the ground for the formal rules that would later define Western art for centuries. The perspectograph, therefore, stands as a beautiful testament to collaboration between the workshop and the study, proving that the hand of the craftsman and the mind of the geometer were essential partners in the march toward realism. This blending of technical precision with creative expression represents a pivotal moment in cultural history. The perspectograph demystified the process of representation, making the skills required for realistic drawing more accessible and less reliant on innate, untrainable talent. It encouraged a more analytical way of seeing, where the world could be broken down into its constituent parts and understood through geometry. This shift in perception echoes the very essence of the scientific mindset that was simultaneously taking root: the belief that nature, for all its apparent complexity, operated on knowable principles that could be revealed through careful observation and measurement. The device used to capture a perfect likeness of a face or a building was in its own way a tool of inquiry as potent as the astrolabe or the quadrant. Its legacy is the entire tradition of illusionistic art that followed, a tradition founded on the powerful idea that even the most fleeting trick of the eye could be captured, mastered, and reproduced through the clever application of a simple grid of strings, forever changing how we see and represent the world around us. In the shadowy corridors of medieval power, where a single intercepted message could topple a throne or bankrupt a merchant empire, the need for secure communication sparked a brilliant fusion of linguistics and mechanics. This gave rise to the cipher wheel, a deceptively simple device that would become the guardian of state secrets and a cornerstone in the long history of keeping information from prying eyes. Imagine two concentric discs, one slightly smaller than the other, both meticulously engraved with the letters of the alphabet. The outer ring might be fixed to a wooden base, while the inner disc could be rotated freely, its letters aligning with those on the outer wheel in a constantly shifting pattern. This elegant tool transformed the art of cryptography from a complex, error-prone process of manual substitution into a swift, reliable, and portable system. A diplomat on a dangerous mission could carry this device in a pouch, and with a quick turn of the inner wheel, render his most sensitive reports into an unreadable jumble of characters, confident that only a recipient with an identical wheel, set to the same starting position, could decipher the true meaning. The most famous implementation of this principle, though from a later period, was the Vijna cipher, a polyalphabetic system that was considered virtually unbreakable for centuries and whose concepts were embodied in these rotating discs. Its true power lay in the use of a key, a pre-shared word or phrase known only to the sender and receiver. To encrypt a message, the user would first align the disks according to the first letter of the key. For example, if the key letter was K, they would rotate the inner wheel until it's sat directly below the outer wheel's K. Then, to encode the first letter of the message, they would simply find that letter on the inner wheel and note the corresponding letter on the outer fixed wheel. For the next letter in the message, they would advance the inner wheel to the next letter of the key and repeat the process. This constant shifting of the substitution alphabet is what made the cipher so formidable. Unlike a simple monoalphabetic cipher, which always replaces a specific letter with another specific letter, this method meant that the same letter in the plaintext message could be represented by different encrypted letters throughout, effectively obliterating the frequency analysis that was the primary tool of any would-be codebreaker of the era. The impact of this tool on medieval and Renaissance statecraft was profound. It empowered kings, popes, and generals to coordinate military campaigns across vast distances without fear that their strategies would be discovered by enemy spies. It allowed ambassadors to send candid reports back to their sovereigns, fostering a new level of diplomatic complexity and intrigue. Merchant guilds used simpler versions to protect the details of trade routes and commodity prices, turning commercial information into a valuable, encrypted asset. The cipher wheel became a symbol of trust and high clearance. To possess one was to be entrusted with the most confidential affairs of state or commerce. Its very existence acknowledged a new, pervasive reality. That information was power, and that power needed mechanical protection. This clever device formalized the ancient art of secrecy, moving it from the realm of clever scribes into the hands of any literate person who could be taught the simple mechanical process of turning a dial. Beyond its immediate practical use, the Cipher wheel's design represents a breathtaking intellectual leap. It is a physical manifestation of abstract mathematical principles, a machine for generating complexity. Each turn of the disk is a step in an algorithmic process, a forerunner of the mechanical computation that would centuries later lead to everything from complex looms to modern computers. In fact, the fundamental logic of the Cipher wheel, using a key to systematically alter a process, is the bedrock of modern digital encryption that secures our online transactions and communications today. The medieval inventors of this tool may not have envisioned the internet, but they perfectly understood the core problem: how to use a shared secret to create a private channel within a public space. Their solution, carved in wood and brass, was a quiet revolution in information security. This mastery of encoded information, of creating a hidden layer of meaning within an ordinary-looking text, beautifully sets the stage for a device that operated on a similar principle of layered revelation. Just as the Cipher wheel used rotation to conceal and reveal true messages, the next instrument used rotating components to conceal and reveal the true positions of celestial bodies, offering a mechanical window into the planned motion of the cosmos itself. While the Cipher wheel mastered the art of concealing information within language, another instrument performed a different kind of revelation, one that laid bare the hidden mechanics of the cosmos for all to see. This was the Equatorium, a device of breathtaking ambition that sought to do for the planets what the Astrolabe did for the fixed stars, to model their complex and wandering paths across the sky without requiring the user to wrestle with the formidable mathematics of Ptolemaic astronomy. Imagine a series of finely crafted brass discs, each one representing the orbit of a planet, all carefully aligned and geared to move in relation to one another. By turning a hand crank or adjusting a series of dials, a medieval scholar could simulate the motion of the heavens over days, months, or even years, watching as the pointer for Mars, Jupiter, or Saturn advanced along its own unique path. This was not just a calculator, it was a physical embodiment of astronomical theory, a working model of the universe that made the abstract principles of epicycles and deference suddenly tangible and comprehensible. The intellectual engine behind this device was the profoundly influential and profoundly complex Ptolemaic system. Claudius Ptolemy's great work, the Almagest, provided a mathematical framework to explain the planet's occasional retrograde motion, the puzzling loop they performed against the backdrop of stars. His solution involved a clever combination of circular motions. Each planet traveled on a small circle called an epicycle, the center of which itself traveled on a larger circle called the deferent. Calculating a planet's position using these concepts required solving a series of intricate trigonometric equations, a task that could take even a skilled astronomer hours of laborious work with pen, parchment, and trigonometric tables. The Equatorium elegantly sidestepped this entire computational nightmare. Its disks and pointers were essentially an analog computer. Their sizes and gear ratios were designed to mechanically solve the very same geometric problems that the equations described. Instead of crunching numbers, the user simply set the date and read the result directly from the instrument's finely engraved scales, transforming a day's work into a matter of minutes. This revolutionary approach to astronomy was largely pioneered and perfected by scholars in the Islamic world, who were deeply engaged in refining and criticizing Ptolemaic models. The 11th century astronomer Abu Ishaq Ibrahim al-Zarqali, known in Latin Europe as Arzashul, is credited with constructing one of the most sophisticated early equatoria, a device that could accurately determine the positions of all 7 known planets. His designs, along with those of other Islamic astronomers, made their way into medieval Europe through translations of Arabic texts in centers like Toledo, Spain. European instrument makers, particularly in France and England, eagerly adopted the concept, crafting their own versions from brass, wood, and even parchment. These instruments became prized possessions in university libraries and the studies of wealthy patrons, symbolizing a commitment to the new learning and providing a powerful hands-on tool for teaching the next generation of astronomers. The Equatorium, in effect, democratized advanced planetary astronomy, breaking down the high mathematical barrier to entry and allowing students to engage directly with cosmic theory. The true genius of the Equatorium lay in its dual nature as both a practical tool and a profound philosophical statement. On a practical level, it was incredibly useful for generating the planetary data essential for creating accurate astrological charts, a major driver of astronomical inquiry in the medieval period. A physician astrologer could use it to quickly find the positions of the planets at the moment of a patient's birth, while a university lecturer could use it to demonstrate the upcoming retrograde of Jupiter to his students. But on a deeper level, the very existence of the Equatorium reinforced a powerful worldview that the universe was a rational, mechanical, and ultimately knowable system. The fact that one could build a physical machine out of brass and gearwork that accurately mimicked the motion of distant celestial bodies suggested that the cosmos itself might operate on similar mechanical principles. This idea of a clockwork universe would become a central motif of the later scientific revolution, and the Equatorium stands as one of its earliest and most evocative precursors. Its legacy is directly visible in the magnificent orreries and planetariums that would follow centuries later. The Equatorium was the conceptual bridge between the static, representative Armillary sphere and the dynamic, mechanical models of the solar system that captivated the Enlightenment. It proved that complex natural phenomena could not only be understood but could also be simulated through clever engineering, a principle that underpins everything from modern weather forecasting to supercomputer climate models. The Equatorium teaches us that sometimes the fastest way to a difficult answer is not through faster calculation, but through a different kind of thinking altogether, through building a physical analog that does the math for you. This brilliant mechanical shortcut for understanding the cosmos creates a fascinating contrast with our next instrument, which served a purpose that was equally profound but far more personal, using the same principles of celestial measurement to anchor the daily lives of individuals within the sacred flow of time. While the Equatorium offered a grand, mechanical vision of the cosmos, another instrument brought celestial measurement down to a deeply personal and spiritual level, weaving astronomy directly into the sacred rhythm of daily life. This was the Horary Quadrant, a specialized and deeply symbolic variant of the familiar quadrant, meticulously designed for a single, profound purpose: to determine the precise times for Islamic prayer. In a faith where the daily schedule is governed by the sun's position, from the Fajr prayer at dawn to the Isha prayer in the evening, this device became an essential bridge between heaven and earth, a tool that translated the silent motion of the sun into a call for devotion. Its design was a masterclass in focused application, stripping away the quadrant's general-purpose scales and instead engraving its surface with beautiful, intricate curves and lines that map directly onto the changing altitude of the sun throughout the year, calibrated to indicate the 5 canonical prayer times without any need for complex calculation or external tables. Operating the Harari quadrant was a ritual in itself, a quiet moment of contemplation that preceded the act of prayer. The user would first align the instrument by sighting the sun along the edge of the alidade, the instrument's sighting rule, allowing the weighted string to mark the sun's current altitude on the engraved scale. But instead of reading a simple angle, their eye would then travel to a series of exquisitely etched arcs, each one representing a different prayer time, and each carefully calculated for a specific period of the solar year. The point where the sun's altitude intersected these arcs would instantly reveal whether it was time for D, Hua the midday prayer, or Asa the afternoon prayer. This elegant system transformed a complex astronomical observation into a simple, almost intuitive act, making it accessible to any faithful individual, from a learned imam in a grand mosque to a merchant in a bustling souk or a traveler pausing by the side of a desert road. It was a personal timekeeper for the soul, ensuring that one's daily obligations to God were met with punctuality and precision, no matter where one found oneself. The cultural significance of this instrument extended far beyond its practical function. Its widespread use across the vast Islamic world, from the shores of Spain to the islands of Indonesia, created a remarkable unity in religious practice. A Muslim in Cordoba using his Harari quadrant and a Muslim in Baghdad using his would be performing their prayers at the same relative moment in the sun's journey, creating an invisible synchrony of devotion across continents. This shared reliance on a scientific instrument for spiritual observance beautifully illustrates the seamless integration of knowledge and faith that characterized the Islamic Golden Age. Astronomy was not seen as a separate, secular pursuit. It was a deeply religious science, a way to understand the grandeur of God's creation and to obey His commandments with greater accuracy. The craftsmanship of these quadrants often reflected this sacred purpose, featuring inscriptions from the Quran, geometric patterns symbolizing the infinite nature of the divine, and prayers engraved lovingly into the brass, turning each instrument into a work of art as well as a tool of science. This harmonious fusion of disciplines finds a powerful parallel in medieval Christian monasteries across Europe, where a different but equally rigid schedule of prayer, the divine office, governed every hour of a monk's life. While they often relied on water clocks or sundials for the nighttime hours, the principles of solar timekeeping were equally vital. The Harari quadrant story, therefore, is not one of isolation but of a shared human impulse to use the tools of science to structure and give meaning to spiritual practice. It stands as a timeless reminder that the drive to understand the natural world and the desire to connect with the divine have often been two sides of the same coin, each enriching and enabling the other. The careful observation required to chart the sun's path for prayer required the same patience, discipline, and reverence as the prayers themselves, making the user of the Harari quadrant both an astronomer and a worshipper in a single, graceful motion. After exploring the celestial and the spiritual, we now turn to a tool that dealt with the most tangible measure of medieval power and prestige, pure, unadulterated wealth. In the bustling marketplace or the royal mint, where the value of a coin was quite literally only as good as the metal it was made from, trust was not a given, it had to be proven. This critical task fell to a device of almost primitive simplicity, yet one whose reliability underpinned entire economies, the touchstone. Imagine a small, smooth, dark slab of stone, typically a hard, fine-grained black quartz like Lydian stone, worn smooth by countless tests. Its unassuming appearance belied its immense importance. An assayer or a merchant would take a coin or a piece of jewelry and vigorously rub it against this stone's surface, leaving behind a thin, faint streak of metal. The true test came next, as they would rub a reference needle, a known sample of pure gold or silver, right beside it. The color, the texture, and even the way the light played on these two streaks, when compared side by side, would reveal the truth about the metal's purity with startling accuracy. This was not a guess, it was a calibrated visual comparison that separated honest currency from clever forgery. The genius of this method lies in its elegant application of material science. Different metals and alloys, when abraded, leave behind streaks with unique characteristics. Pure 24-karat gold produces a rich, warm yellow streak that is unmistakable. But if that gold is alloyed with cheaper copper, the streak will take on a noticeably reddish or brassy hue. If it's cut with silver, the streak will appear paler and cooler. The touchstone master, often a guild-sanctioned expert, would have a full set of reference needles representing various levels of fineness, from 23 carats down to 18 or lower. By comparing the unknown sample streak against this graded scale, they could estimate its carat value with a precision that was more than sufficient for commercial purposes. For an even more refined test, a drop of Aqua Forte's nitric acid might be applied to the streaks. The acid would react differently based on the composition. It might vigorously fizzle and dissolve a streak from a base metal like copper, while leaving a pure gold streak largely unaffected. This combination of mechanical and chemical testing created a robust, two-step verification process that was incredibly difficult to fool. This simple tool's role in maintaining economic stability cannot be overstated. In an era before centralized banking and standardized national coinage, currency was a chaotic affair. Coins from different realms, often clipped or sweated to remove precious metal, circulated freely. A merchant accepting payment or a mint official producing new coinage had to be absolutely certain of the value in their hands. The touchstone was the ultimate arbiter. Its verdict could prevent a kingdom's currency from being debased, protect a trader from being swindled, and ensure that contracts and taxes were paid in good faith. It was the foundation upon which trust in the monetary system was built, a portable, affordable, and highly effective lie detector for metal that allowed commerce to flourish across cultures and languages. Its presence on every major merchant's table and in every mint was a silent promise of fairness, a guarantee that the value everyone agreed upon was in fact real and present. Beyond the marketplace, the touchstone also became a powerful cultural metaphor, a concept that persists in our language today. To call something a touchstone is to describe a fundamental standard against which other things are judged for their quality, authenticity, or value. This linguistic legacy is a direct tribute to the instrument's profound cultural impact. It represented an objective, unwavering truth in a world often clouded by deception and subjective opinion. Philosophers and writers adopted the term to describe the core principles that could test the validity of ideas, just as the stone tested the purity of metal. This dual identity, as both a physical tool and a philosophical concept, highlights how deeply embedded this device was in the medieval mindset. It was a symbol of integrity, a reminder that true value could withstand rigorous testing and comparison. The touchstone's enduring legacy, both literal and metaphorical, demonstrates how a perfectly designed tool can transcend its immediate practical function to become a cornerstone of both commerce and culture, providing a stable foundation in a world of fluctuating values. From the precise purity tests of the touchstone, we now tune our ears to an entirely different kind of investigation, one that sought to measure not the quality of metal, but the invisible behavior of sound itself. In the quiet halls of medieval monasteries and the workshops of curious philosophers, a new class of instruments emerged dedicated to the mysteries of acoustics. Among these, the echometer stands out as a particularly fascinating device, a tool designed to capture and quantify one of sound's most elusive properties, its reflection. Imagine a long, narrow tube, perhaps crafted from wood or metal, with a carefully measured interior and a mouthpiece at one end. A scholar would speak or create a sharp sound into this tube, directing it towards a distant surface, and then listen intently for the returning echo. By timing the delay between the initial sound and its rebound, often using the steady drip of a water clock or the pulse of their own heartbeat as a rough metronome, they could estimate the distance to the far wall or object. This simple experiment was a groundbreaking foray into the physics of sound waves, transforming an everyday phenomenon into a measurable scientific event. The true ambition behind these acoustic experiments was far grander than mere distance measurement. Medieval thinkers, inspired by the ancient Greeks, were deeply curious about the fundamental nature of sound itself. They understood it as a vibration, a physical wave traveling through the air, and they used devices like resonating chambers, specialized rooms or hollow vessels with precisely calculated dimensions to explore its behavior. By singing a steady note into a chamber and carefully adjusting the pitch, they could find a specific tone at which the entire space seemed to sing back, the sound waves amplifying each other through the principle of resonance. This dramatic effect, where a certain frequency caused the very air in the room to vibrate in sympathy, was both magical and deeply instructive. It revealed that sound was not some mystical force but a physical energy that interacted with the material world in predictable, measurable ways. These chambers became laboratories for understanding harmony, dissonance, and the mathematical relationships between different pitches, directly linking the science of acoustics to the art of music. This hands-on exploration had profound and practical implications, particularly for the most ambitious architectural projects of the age, the great Gothic cathedrals. The designers of these vast, soaring spaces were intuitively, and then deliberately, applying the principles of acoustics that devices like the echometer helped to reveal. They understood that the shape of a vaulted ceiling, the curve of an apse, or the texture of a stone wall could dramatically affect how sound carried from the pulpit to the pews. A rounded dome might focus sound like a whispering gallery, allowing a priest's words to be heard clearly on the far side of the choir, while an overly flat, hard surface could create a confusing jumble of reverberations. By experimenting with scale and materials, these master builders became unsung pioneers of architectural acoustics, ensuring that the sacred chants and sermons that filled their creations would be experienced with clarity and emotional power, their invisible waves shaped as carefully as the stone itself. The legacy of these rudimentary echometers and resonating chambers is literally all around us. They represent the first steps toward a world where sound is not just heard but engineered. The principles of reflection, absorption, and resonance that medieval scholars tinkered with are the exact same ones used by modern audio engineers to design concert halls, recording studios, and even the speakers in a home theater system. Their work established that the behavior of sound could be mapped, predicted, and manipulated through geometry and mathematics. This relentless curiosity about an invisible force, a curiosity that used simple tubes and chambers to ask profound questions about wave behavior, perfectly sets the stage for the final instrument in our journey, a device that mapped a force even more mysterious and fundamental than sound, the invisible pull of the earth itself. Among all the instruments that sought to measure the visible world, none was as profound as the one that mastered an invisible force, the mysterious pull of the Earth's magnetic field. This was the Lodestone compass, a device so transformative that it effectively redrew the map of the known world, turning the vast, terrifying oceans into charted highways for exploration and trade. Its principle was one of beautiful simplicity, a slender sliver of iron, carefully stroked against a naturally magnetic lodestone until it was itself magnetized, then delicately suspended from a silk thread or floated on a reed in a bowl of water. Freed from friction, this needle would tremble, sway, and then steadfastly align itself along a north-south axis, its unwavering pointer offering a constant, reliable reference to direction regardless of the weather, the time of day, or the visibility of the stars. For the first time in human history, navigators possessed a guide that worked equally well under a blazing sun or in the pitch black of a storm-tossed night, a tool that made the daunting unknown feel suddenly knowable. The journey of this revolutionary technology is a classic tale of medieval globalization. While the magnetic properties of lodestone were known to the ancient Greeks and Chinese, it was in China during the Song dynasty that the first true navigational compass was developed, initially used for geomancy and land surveying before its potential at sea was realized. Knowledge of this marvel then traveled westward, likely carried along the bustling Silk Road or by Arab traders plying the Indian Ocean. Islamic scholars and instrument makers in the Middle East eagerly adopted and refined the design, often embedding the magnetized needle into a beautifully crafted brass box with a glass cover to protect it from the elements. By the 12th century, this technology had reached Europe, where it was quickly recognized as a game-changer. Mediterranean sailors, who had long been constrained to fair-weather coastal sailing, began to integrate the compass with their existing portolan charts and wind roses, creating the first comprehensive navigational systems that allowed for true open-water voyages. This cross-continental collaboration, from Chinese innovation to Islamic refinement to European application, showcases the interconnectedness of the medieval world and how a single tool could catalyze a shared leap forward in human capability. The true magic of the compass lay in its integration with another instrument we've already explored, the wind rose. This partnership created the iconic compass rose that still adorns our maps today. The floating magnetic needle was placed at the center of a circular card painted with the 32 points of the wind, north, north by east, north, northeast, and so on. As the ship yawed and pitched, the card would rotate with the vessel, but the needle held fast, pointing to magnetic north. A navigator could now glance down and instantly see the exact heading of his ship in relation to the fixed north. This simple visual readout transformed navigation from an art of estimation into a science of precision. A captain could now chart a room line, a course of constant compass bearing, and maintain it for days or even weeks, confident that he was moving in a straight line toward his destination rather than sailing in a wide, disorienting arc. This ability to hold a straight course across featureless water was the key that unlocked the age of exploration, making journeys across the Mediterranean, around Africa, and eventually across the Atlantic not just possible but repeatable and reliable. The impact of this reliability on the medieval psyche and the course of history is almost impossible to overstate. Before the compass, ocean travel was an act of profound courage bordering on recklessness, limited to short hops between visible landmarks. The compass annihilated this limitation. It empowered explorers to venture beyond the edge of the map, driven by the unwavering faith that this little sliver of metal would always guide them home. It was the silent, indispensable partner on the caravels of Prince Henry the Navigator's captains as they edged down the West African coast, and it was aboard the ships of Christopher Columbus as he sailed into the utter unknown of the Western Atlantic. The compass did not just guide ships, it guided ambition, fueling the dreams of monarchs, merchants, and adventurers alike. It ushered in an era of unprecedented cultural and economic exchange, weaving together the continents through trade routes that carried spices, silks, ideas, and unfortunately, diseases, forever altering the demographic and political landscape of the entire planet. This humble instrument, by making the invisible visible, quite literally changed the face of the world, setting the stage for a globalized existence that defines our modern era. Tucked away in the margins of magnificent medieval manuscripts, amid the flowing Latin script and vibrant illuminations, lies what might be the most ingenious and accessible computer of the age, the volvelle. This was not a tool of brass or bronze, but of parchment and thread, a breathtakingly intricate assembly of rotating paper discs, carefully cut and layered, that transformed a static book into an interactive calculating machine. To turn these delicate dials was to physically engage with knowledge, to slide a window over a calendar or align a zodiac sign with a planet's path, watching as a complex astrological chart or a medical diagnosis revealed itself through the clever alignment of holes and carefully inked data. This was technology stripped down to its most elegant essentials, information that could be manipulated not with keys or code, but with the simple, intuitive turn of a hand, making the most sophisticated concepts of the medieval world tangible to any literate person who knew the secret of its operation. The construction of a single volvelle was a masterclass in meticulous planning and precise craftsmanship. A scribe or scholar would begin with the base layer of parchment, often a permanent table of information like a star chart or a calendar of saints' days. Then, using a sharp knife, they would carefully cut out one or more additional discs, each slightly smaller than the last, ensuring they could rotate freely without tearing. These moving parts were attached to the base page with a tiny thread or a cleverly fashioned parchment pivot, a delicate hinge that had to be strong enough for repeated use yet gentle on the fragile page. Each layer was then meticulously inscribed with its own set of data, perhaps the phases of the moon on one disk, the signs of the zodiac on another, and the days of the month on a third. The user's task was to align these elements, turning the disks until the correct information showed through a specially designed aperture or window cut into the top layer. The final result was a dynamic, multi-layered diagram that could answer a specific question based on the variables input by the reader, a paper-based algorithm centuries before the term was ever coined. This elegant design found applications across the entire spectrum of medieval knowledge, democratizing expertise in ways we can still appreciate today. In the realm of medicine, a volvelle could serve as a diagnostic aid. A physician might turn a disc to align a patient's birth date with the current position of the moon, believed to influence bloodletting and other procedures, thereby determining the most auspicious day for surgery or administering a remedy. For an astrologer, a more complex volvelle could calculate the precise hour of a planetary conjunction or the ascendant sign for a client's nativity chart, tasks that would otherwise require laborious manual calculation with trigonometric tables. Even the practical matter of telling time at night could be managed with a volvelle-based nocturnal, its paper dials replacing the wooden ones carried by sailors. This transformative power, turning a passive reader into an active participant, meant that a single book could contain not just knowledge, but the very tools needed to generate new knowledge from it. Perhaps the most stunning examples of this art form are found in the works of the 13th century English monk and philosopher Roger Bacon, and the magnificent 14th century manuscript of Giovanni da Dondi's astronomical writings. These were not simple gadgets but sprawling, multi-component systems of volvelles that sprawled across entire pages, with dials within dials and pointers that swept across scales of stunning complexity. They represent the absolute pinnacle of the manuscript as an interactive object, a book that was also a workshop, an observatory, and a laboratory. Their existence speaks to a world where the boundaries between disciplines were beautifully blurred, The same mind that contemplated theology might also design a volvelle to calculate eclipse times, and the same hand that painted a heavenly angel might also carefully cut the rotating disk that mapped its celestial domain. This fusion of intellectual curiosity, artistic flourish, and technical precision is the volvelle's most enduring legacy. In many ways, the humble volvelle is the perfect symbol to conclude our journey through these 26 instruments. It requires no rare metals, no advanced metallurgy, or complex gear-cutting tools. Its power comes from creativity, from a profound understanding of information design, and from the simple yet revolutionary idea that a user should be able to have a conversation with their data. It is a direct paper and ink ancestor to the circular slide rules, the rotating warning calculators in early aircraft, and even the graphical user interfaces of our modern computers. Every time we adjust a digital slider to see how a change affects a graph or spin a 3D model on our screen, we are engaging in a form of interaction that the volvelle pioneered. It reminds us that the heart of innovation isn't always found in the most complex machinery, but often in the most clever arrangements of the materials we have at hand, proving that even the simplest technology, when paired with human ingenuity, can unlock the secrets of the universe. What we have witnessed across these 26 instruments is far more than a collection of historical curiosities. It is the very bedrock upon which our modern scientific world was built. Each device, from the grand Armillary sphere to the humble touchstone, represents a profound leap in humanity's ability to measure, understand, and ultimately shape its reality. They were not isolated inventions but nodes in a vast, interconnected web of global knowledge, embodying a spirit of relentless inquiry that effortlessly transcended the cultural and geographical boundaries we so often emphasize today. This was a period where a design perfected in Baghdad could be refined in Cordoba and then put to use in a Parisian university, where Chinese advancements in magnetism would eventually empower European explorers to sail across oceans. This free flow of ideas, facilitated by trade routes and scholarly exchange, reminds us that innovation has always been a collaborative, international endeavor, a silent conversation conducted in the universal languages of mathematics, observation, and craftsmanship. The legacy of these tools is etched into the DNA of every modern discipline they helped to birth. The precise angular measurements of the quadrant are the direct ancestors of the theodolites and GPS systems that map our world today. The mechanical predictability of the Equatorium and the water clock's regulated flow established the fundamental principle that natural phenomena could be modeled and predicted through machinery, a concept that culminated in the clockwork universe of Newton and the computers of our own era. The Alembic's transformative processes laid the essential groundwork for modern chemistry, moving experimentation from philosophical speculation into the realm of controlled, repeatable practice. Even the perspectograph's simple grid, which taught artists to see the world as a series of measurable relationships, prefigured the entire scientific method of breaking down complex problems into smaller, solvable parts. These were not just tools for their time, they were the first prototypes, the foundational algorithms, for the world we now inhabit. Perhaps the most poignant lesson these instruments offer us today lies in their elegant sustainability and their deeply interdisciplinary nature. Crafted from locally available materials like wood, brass, and parchment, they were designed for longevity and repairability, a stark contrast to our modern culture of disposable technology. But more importantly, they refuse to be categorized. Is the astrolabe an instrument of astronomy, navigation, or timekeeping? The answer is yes. Does the monochord belong to the musician, the mathematician, or the philosopher? It belongs to all of them. These tools stand as powerful rebukes to the hyper-specialization of our current age, demonstrating that the most profound breakthroughs occur at the intersections between fields. The medieval scholar saw no divide between the science of the stars and the faith of the divine, between the beauty of art and the precision of geometry. In rediscovering these instruments, we are invited to reclaim that holistic way of seeing, to break down the artificial walls between disciplines and recognize that the greatest challenges of our time, from climate change to public health, demand precisely this kind of integrated creative thinking. Their eventual disappearance from common use is not merely a footnote in history. It is a cautionary tale about the fragility of knowledge. Many of these marvels were forgotten not because they were obsolete, but because the specialized crafts required to build them were lost. The manuscripts that explained their use crumbled away, or newer technologies simply overshadowed their unique virtues. This loss reminds us that progress is not a straight, inevitable line upward. Peaks of brilliance can be achieved, forgotten, and then have to be painstakingly rediscovered centuries later, as the story of the Antikythera mechanism so powerfully illustrates. It urges a sense of stewardship, a responsibility to preserve not just the physical artifacts of our own era, but the intricate, often tacit knowledge required to create and use them. In an age of digital abstraction, these tangible instruments reconnect us with the physical intuition and hands-on skill that are the essential partners to theoretical brilliance, offering a timeless lesson in where true understanding ultimately resides. From the intricate star charting Astrolabe to the interactive paper computers known as volvelles, these 26 marvels did far more than just measure the world. They fundamentally tuned it, harmonizing meticulous observation with masterful craftsmanship and an insatiable curiosity that transcends time. They stand as a powerful testament to humanity's relentless, universal drive to understand the universe, not through passive contemplation, but through active, hands-on engagement. What this journey reveals is a profound truth about progress itself. It is rarely a straight line of inevitable advancement. More often, it is a spiral, built upon layers of forgotten innovations, clever ideas that were sidelined by new technologies or simply lost to history's upheavals. By pausing to rediscover these tools, we gain a crucial and humbling perspective on our own breakneck technological journey. We are reminded that our digital age, for all its wonders, did not emerge from a vacuum, but is instead the direct inheritor of a 1,000-year conversation between the human mind and the material world. This perspective becomes not just interesting, but essential, as we confront the unique challenges of our modern era. Issues like climate change and ecosystem collapse demand solutions that are not only technologically sophisticated, but also sustainable and deeply integrated with natural systems. The medieval toolkit offers a powerful inspiration here. These instruments were crafted from local, durable materials: wood, brass, parchment, and were designed for repair and longevity, not for disposal. They operated on principles of balance and cyclical patterns, mirroring the very natural world they sought to measure. In an age of digital overload and constant connectivity, they also whisper a lesson in focused simplicity. Using an astrolabe or a nocturnal requires patience, quiet observation, and a deep connection to one's immediate environment, a stark and beautiful contrast to the fragmented attention demanded by our screens. They challenge us to blend the undeniable power of our modern sophistication with the elegant, sustainable simplicity of the past, to create a technology that serves both humanity and the planet. This is where the conversation turns to you. I am deeply curious to know which of these instruments captured your imagination most powerfully. Was it the cosmic complexity of the Antikythera mechanism, an ancient computer lost beneath the waves? Or perhaps the elegant practicality of the Nocturnal, a sailor's steadfast companion under the stars, Could it have been the Monochord, which made the mathematics of music tangible, or the humble touchstone, the guardian of economic trust? Share your thoughts in the comments below. Let's continue this exploration together and learn from each other's perspectives. If you've enjoyed this journey into history's hidden workshops and want to join us for more, please subscribe to the channel and hit the bell so you don't miss our next adventure into the past. Remember, these forgotten tools are more than just relics. They are a timeless reminder that the past holds invaluable keys to our future. By listening to their lessons, we can better understand our present and unlock a wiser, more harmonious path forward. Let's